Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. Look up on a clear night, far from the city lights. Above you stretches an endless dark ocean sprinkled with stars. The longer you gaze, the more stars appear, as if the universe is revealing a secret tapestry. Each star is a sun, distant and powerful. Our own sun is just one among hundreds of billions of stars in our galaxy. And our galaxy, the Milky Way, is one among trillions. In fact, astronomers estimate there may be 2 trillion galaxies in the observable universe. Try to imagine that. 2 trillion island universes, each brimming with stars beyond counting. If you could snap your fingers and count one galaxy per second, you'd be counting for over 65,000 years just to list them all. Within those galaxies are countless worlds. Some scientists say as many as 6 billion Earth-like planets may orbit stars in our Milky Way alone, and perhaps 12 quintillion across the cosmos. 12 quintillion Earths, 12 quintillion possibilities. The scale of space truly defies comprehension. It's a void, a vastness, but also a canvas of nearly infinite possibilities. Floating on a tiny rock called Earth, we humans have always felt small under this sky. Tiny, yet special, because we can ponder it. We can ask, what is all this? What is the nature of space, of reality? How amazing that the universe is comprehensible enough that we can study it, yet mysterious enough to inspire wonder. As the famous astronomer Carl Sagan once said, the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. We are made of atoms forged in long, dead stars, now come alive to gaze back at the sky. Through us, the universe questions its own existence. And one of the most profound questions we can ask is, are we even real? Could all this enormity, this grand cosmos, be an elaborate illusion or construction? Could we, our lives, our planet, our universe, be part of a grand cosmic simulation? That question sounds like science fiction, yet it has leapt from the pages of novels and movie scripts into serious scientific and philosophical debate. What if our reality is not the base reality? What if it's a program, running on some unfathomably complex computer, created by entities beyond our realm of existence? It's an idea that can feel both thrilling and unsettling, the simulation hypothesis. In essence, this hypothesis suggests that what we perceive as the physical universe, including space and time, might be an artificial simulation, like a high-resolution virtual reality designed by an advanced intelligence. In other words, maybe we are living in someone else's computer program. Pause for a moment and really consider that. The ground beneath your feet, the air you're breathing, the light from those distant stars, could all of it be code? If it were true, if everything we know is part of a simulation, how would we know? Would it even matter to us inside it? And who, or what, might be the programmer of the cosmos? These questions take us to the edge of what science can speculate and what philosophy can ponder. They force us to confront the nature of reality from a perspective that is both deeply cosmic and intensely personal. Tonight, we'll embark on a journey through this maze of ideas. We'll wander the vastness of space, marveling at its wonders, and we'll delve into the simulation hypothesis, examining why some prominent thinkers believe it might be true and why others remain skeptical. We'll touch on ancient philosophical puzzles and cutting-edge scientific experiments. We'll meet the scientists and philosophers wrestling with these questions, from those studying the quantum underpinnings of reality, to technologists pushing the boundaries of virtual reality, to philosophers questioning whether real and simulated are even meaningful distinctions. Along the way, we'll peer into the very code of the universe and see if there are hints that reality has a designer, and we'll imagine what it would mean for our lives, our purpose, our future, if we are indeed characters inside a grand cosmic simulation. This idea, questioning the reality of reality, is not entirely new. Long before computers and simulations, humans sensed that the world might not be exactly as it appears. Over 2,000 years ago, the Greek philosopher Plato proposed a famous allegory. Imagine people who have lived chained in a dark cave all their lives, Plato said, facing a blank wall. All they ever see are shadows cast on that wall, shadows of objects behind them, objects lit by a fire. Those shadows are their entire reality. They give them names. They think they're real things, but they're just projections, mere silhouettes of something truer. One day, a prisoner is freed and stumbles outside into the dazzling sunlight. For the first time, he sees the full, rich world beyond the cave and realizes the shadows were just a pale imitation of reality. Plato used this allegory of the cave to discuss knowledge and enlightenment, but it resonates eerily with the simulation idea. If we are like those cave prisoners, then our day-to-day world might be the shadow play, while the true reality exists outside our current perception. Could it be that we are living in a cave of sorts, seeing shadows and mistaking them for the whole of existence? Across cultures, similar notions appear. In ancient Chinese philosophy, Zhuangzhou wrote of a vivid dream in which he was a butterfly fluttering about. In the dream, he was happy, unaware of any other life. When he awoke, he found himself lying in bed as a man, but then he wondered, was he a man who had dreamed he was a butterfly, or a butterfly now dreaming he was a man? This butterfly dream story captures a deep puzzle. How can we know if our experience right now is real, or some kind of dream or illusion? Likewise, in Hindu philosophy, the concept of Maya describes the world as an illusion, a sort of cosmic play. And the French philosopher René Descartes, in the 17th century, famously imagined an evil demon that could be tricking him with an illusory world, an early pondering of a virtual reality created to deceive the senses. Descartes realized the only thing he couldn't doubt was his own mind's existence, which is not so far from the simulation question. If everything were simulated, the one thing we might be sure is real is our own consciousness experiencing it. We humans have a long history of questioning reality, but the simulation hypothesis, as we discuss it today, took these age-old questions and reframed them in the context of modern technology and cosmology. It's as if the ancient philosophical doubts met the era of computers and video games and found a new form. A key moment in popular culture was the release of The Matrix in 1999, a film that riveted audiences with its depiction of humans unknowingly trapped in a perfectly simulated world. People plugged into a virtual reality, living in a shared illusion while their bodies lay elsewhere, asleep. The Matrix wasn't the first story of its kind, but it presented the idea so powerfully that it became a cultural touchstone for this concept. Suddenly, the question, what if we're in a simulation, moved from esoteric philosophy to everyday conversations. After watching Neo choose between the red pill and blue pill, a whole generation had a reference point for discussing the nature of reality. Just a few years after that film, in 2003, a philosopher named Nick Bostrom at Oxford University gave the simulation idea a rigorous academic form. Bostrom wrote a paper with a title that cuts straight to the core: Are you living in a computer simulation? In it, he proposed a sort of logical argument, a trilemma. It goes something like this. 1. Almost all civilizations at our stage of technological development go extinct before they ever become technologically posthuman. In other words, maybe it's incredibly rare to survive long enough to create the kind of computing power needed for world-sized simulations. 2. If a civilization does reach that advanced stage, perhaps almost none of them would be interested in running simulations of minds like their ancestors. Maybe it's simply not done. whether for ethical reasons or lack of interest. 3. If the first two propositions are wrong, then the number of simulated conscious beings would far, far exceed the number of original beings. And if that's the case, the odds are that we ourselves are among the simulated minds, not the original biological ones. Bostrom argued that at least one of those three must be true. Either we're doomed to never reach that advanced stage, or we'll reach it, but never simulate worlds with conscious beings, or we're almost certainly in a simulation right now. Importantly, if you think there's any significant chance that advanced civilizations would run such simulations, then you have to admit the possibility that we might be in one. To put it another way, unless we go extinct or never bother to use our future computers this way, it's quite likely that reality as we know it is a digital illusion. That's the unsettling logic Bostrom presented. He even concluded, somewhat playfully yet provocatively, that the belief that there is a significant chance that we will one day become posthumans who run ancestor simulations is false, unless we are currently living in a simulation. In simple terms, we can't have it both ways. We can't both expect our descendants to create loads of simulated worlds and also assume we're in the one real world. If creating simulated universes becomes possible and common, then statistically, our own reality is probably one of the many simulations rather than the one original. This argument hit the scholarly world like a jolt. It was a serious professor, not a Hollywood director, suggesting this mind-bending scenario in earnest. And it came at a time when computing power was growing exponentially, and our own simulations, think computer games, virtual reality experiments, AI programs, were becoming more impressive every year. Bostrom's paper gave a sort of credibility to an idea that, until then, was mostly science fiction. It moved the conversation into journals and conferences. People began to debate, not just, could this be true, but what evidence would there be, and how would this change things? It didn't stay in academia. The idea spilled out into tech companies, into late-night dorm room discussions, into Reddit forums and YouTube channels. Even major public figures started taking it seriously. Perhaps the most famous among them is entrepreneur Elon Musk, known for his ventures in electric cars and space travel. Musk has repeatedly talked about the simulation hypothesis. In 2016, speaking at a conference, he put it in his characteristically blunt terms. There's a 1,000,000,000 chance we're living in base reality, meaning he thinks the odds that our reality is the original reality are almost zero. In other words, Elon Musk believes it's extremely likely that we are living in some kind of computer simulation. That statement grabbed headlines around the world. Here was one of the most high-profile innovators on the planet, casually asserting that everything we experience might be artificial. Musk's rationale was simple. Look at the trajectory of video games. In the 1970s, we had Pong, 2 rectangles and a dot. Today, we have hyper-realistic 3D simulations with millions of players in richly rendered worlds and virtual reality technology that can trick our senses for a time. Given another few decades or centuries, the argument goes, it's inevitable that our technology will produce simulations indistinguishable from reality. If we have that potential, then perhaps some other civilization in the universe already achieved it. And if even one civilization did, the number of simulated universes could be astronomically large. So from Musk's perspective, the math makes it hard to believe we are the one lucky draw that is actually real. He's not alone. Astrophysicist Neil deGrasse Tyson, a science communicator who hosts TV shows and podcasts, has said he thinks there's a very high chance the universe is a simulation. At a debate in 2016, Tyson suggested the likelihood might be better than 50-50 that we live in a simulation. Philosophers like David Chalmers and physicists like Max Tegmark have also entertained the idea in public discussions. Suddenly, the simulation hypothesis has moved from a fringe idea to a topic discussed by scientists at prestigious forums. In fact, the American Museum of Natural History held an entire panel debate on it, with experts from different fields. One journalist described that debate, noting that philosophers, physicists, technologists, and, yes, comedians are all grappling with the idea. It has, in a sense, become mainstream speculative thought. But let's step back a moment. Is there any evidence for this idea, or is it all circumstantial and philosophical? Why would serious people even consider that we might detect the telltale signs of a simulation? To explore that, we need to delve into the nature of physical reality itself, into space, time, and the quantum realm, and see if our universe behaves the way we'd expect a base reality to behave, or if it has quirks more suggestive of a programmed environment. First, consider the nature of space. We usually think of space as simply emptiness. You might picture the void between stars as a silent, cold nothingness. But in physics, space is not truly empty. It has properties. It can bend, ripple, and even boil, with tiny particles popping in and out of existence. According to Einstein's theory of general relativity, space is like a fabric that can stretch and curve. Massive objects like stars and black holes warp this fabric, which is what we feel as gravity. Space, in this view, is dynamic. It's not just an empty stage where things happen, it's part of the actors. When we observed gravitational waves from colliding black holes for the first time in 2015, it was literally space itself trembling, like a pond rippling when a stone is dropped. This is a far cry from the simple nothingness one might assume space to be. Now, zoom down to the tiniest scales, and space gets even weirder. In quantum mechanics, even what we call a vacuum seethes with activity. Particles and antiparticles can spontaneously appear in pairs, exist for a fleeting moment, and annihilate each other. A phenomenon allowed by the quantum rules, as long as it's brief. This isn't science fiction. It's been experimentally observed. If you think about it, this is almost like the universe has a constant background computation running, even when nothing is there. It's as if the simulation never truly idles. There's always some processing happening in the vacuum of space, a constant quantum hum. What about the size of space? The observable universe, the part of the cosmos we can in principle see, extends about 46 billion light-years in every direction from us. We often say 13.8 billion years old, but due to expansion, the radius is larger in light-years, and that's just what's observable. Space could be much larger, potentially infinite. If a simulation were to recreate such a vast space in full detail everywhere, the amount of information would be mind-boggling. Could any computer, even one built by gods or advanced aliens, simulate 2 trillion galaxies worth of stars, planets, and particles? It seems intractable. But if we were inside a simulation, there might be ways to cheat and not simulate everything at once. Think of how video games work. When you're playing a game, the computer or console isn't rendering the entire game world at high resolution all the time. It's only rendering what the player is currently seeing or experiencing. Turn away from a scene, and the game might stop calculating it until you turn back. Some have suggested that a universe simulation might do something similar, only calculate details as needed. This ties into one interpretation of quantum physics that's frequently mentioned in the context of simulations: the idea that observation seems to play a role in how quantum events resolve. There's a famous experiment, the double slit experiment, where particles are fired at a screen with 2 narrow slits. If you don't observe which slit a particle goes through, the particle acts like a wave of possibilities, going through both slits and creating an interference pattern on a detector screen, as if it interfered with itself. But if you set up a detector to watch the slits, the interference pattern disappears. The particle behaves like a single, well-defined object that went through one slit or the other. Simplifying a lot, the outcome changes depending on whether it's observed. To many, this suggests that reality decides on an outcome only when it has to. when an observation is made. This is a cornerstone of quantum mechanics, often summed up as the observer effect. Now, some physicists will caution that it's not that consciousness causes the change per se, just the interaction with a measuring device. But the philosophical interpretation lingers. Perhaps things aren't determinate until they need to be. If you were designing a simulation, that's actually a smart way to save resources. Don't calculate something until someone tries to look at it. In a way, the universe already behaves like that at the quantum level. It's as if there's a level of reality that's in potential form, a haze of probability, and it becomes concrete only upon interaction. Could that be the sign of a rendering engine at work? As Tyson and his comedian colleague Chuck Nice quipped on Star Talk, maybe that's why we have the speed of light limit in our universe. Perhaps the simulation doesn't allow anything to travel faster than light, because then you could get to another star or galaxy faster than the program could load the details. In their playful exchange, Chuck Nice suggested, maybe that's why we can't travel faster than the speed of light, because if we could, we'd be able to get to another galaxy before they can program it. And Tyson added with a laugh, so the programmer put in that limit. It's a joke, but it perfectly illustrates how a computational constraint could manifest as a law of physics. Our cosmic speed limit might be akin to the draw, distance in a video game, preventing us from moving too fast for the simulation to keep up. Let's think about other hints. Some scientists have looked for signatures of discretization in space, essentially evidence that space is not continuous, but made of tiny pixels or chunks, like a digital grid. If the world is simulated, it might be running on a lattice or grid at the smallest scale. In our current physics, we have the concept of the Planck length, which is far smaller than anything we can directly measure. It's often thought of as a scale at which classical ideas of space break down and quantum gravity might take over. If space were truly pixelated, the Planck length might be the size of the pixels. A few researchers have proposed experiments to detect this. Dr. Zohreh Davoudi, a physicist at the University of Maryland, has discussed how, if space-time is discrete, there could be slight changes in how high-energy particles travel across cosmological distances. For instance, we might detect a tiny preferred direction or an upper limit in the energy of cosmic rays because of the underlying grid. Imagine if you tried to draw a perfectly straight, extremely long line on a pixelated screen. At some point, the discreteness might show anomalies. Davoudi specifically noted that if space-time is on a lattice for the simulation's sake, extremely energetic particles might not behave exactly as expected in a smooth continuum, possibly revealing a break in a symmetry-like rotation. So far, no such anisotropy in cosmic rays has been observed. If one were, it would be intriguing, though not absolute proof of a simulation. But the fact that physicists are even contemplating such tests shows how seriously the idea is being taken. Another striking piece of maybe evidence came from James Gates, a theoretical physicist known for his work in supersymmetry. Gates found something unexpected in the equations he was studying. Deep in the mathematical framework of certain supersymmetric models, he discovered equations that are identical to those used in computer error correcting codes. Error correcting codes are algorithms programmers use to ensure data isn't corrupted. Basically, they help systems self-correct mistakes. They are, as Gates put it, what make browsers work, allowing digital information to transmit reliably. So, it was quite startling to find them knitted into the fundamental equations describing how particles and forces might work. Gates said, "I no longer can say that people like Max Tegmark are crazy." Upon realizing this, implying that seeing something so digital, looking in the bedrock of physical law gave him pause. He mused that finding such code in nature's equations, if nature weren't a simulation, would be an extremely unlikely coincidence. Does that mean the universe is a computer program? Not necessarily. It could be that our mathematics just happens to take that form, or perhaps there's a deeper reason for those codes that has nothing to do with actual computing. But it's tantalizing details like this that make scientists raise an eyebrow. It's as if you were walking through a forest and found a computer chip lying on the ground. You'd wonder, is there an intelligence at play here, or is it just an odd-shaped rock that happens to look like a chip? Cosmologist Max Tegmark, whom Gates referenced, has pushed an even broader idea, that the universe fundamentally is mathematical. Tegmark often points out that the more we study nature, whether it's the motion of planets or the behavior of subatomic particles, we find that mathematics describes it with uncanny precision. The laws of physics can be written in equations. They have symmetry and structure, much like a code. Tegmark's perspective is that perhaps the universe isn't just described by math, it is math in a very real sense. If one were a character in a video game, he notes, at some point you might notice the strict mathematical rules of your world and suspect there's an underlying code. Our scientists, by uncovering equations, might just be reading bits of the cosmic source code. This doesn't prove a programmer in the usual sense. Tegmark is careful to frame it as the universe being a mathematical structure on its own, but it certainly rhymes with the simulation narrative. After all, what is code, if not mathematics, implemented in a machine? So from the quantum behavior suggesting on-demand rendering, to potential spatial pixels at Planck scales, to literal error, correcting codes popping up in theoretical physics, the universe has some hints that tickle the mind. None of these are smoking guns. For every intriguing clue, skeptics can offer alternative explanations, but they add up to a picture of a universe that is surprisingly information-like. The physicist John Wheeler once coined the phrase "it from bit," meaning that at a fundamental level, everything may arise from binary choices, from information bits. More and more, our best theories of physics speak in terms of information. Black holes, for example, are often described by how they store information on their event horizons. Quantum entanglement is being investigated as the possible pixel glue of space-time itself in some modern theories. Scientists are exploring the idea that space-time geometry might emerge from patterns of entanglement, essentially from information networks. It's almost as if the universe behaves like a giant information processor. And if so, one can't help but ask, who or what is processing that information? Is it just the universe being the universe? Or is it a computer built by something beyond it? Now, let's take a step further out and look at a completely different line of thinking, the Fermi paradox and the eerie silence of the cosmos. In our opening, we talked about the vastness of space and the countless planets that likely exist. Given those numbers, many scientists believe that life, and eventually intelligent life, should have arisen in many places across the cosmos. Even if a fraction of those 12 quintillion Earth-like planets developed life, and a fraction of those developed intelligent civilizations, there ought to be many alien civilizations out there, some perhaps far older and more advanced than us. This reasoning is encapsulated in the Drake equation, which is a probabilistic formula to estimate the number of communicative civilizations in our galaxy. Depending on what numbers you plug in, you might predict anything from 0 to thousands of civilizations. But many reasonable estimates suggest the galaxy should be home to several at least, and the universe at large, many more. So physicist Enrico Fermi famously asked, "Where is everybody? If life is common, why haven't we seen any evidence? No confirmed signals, no spacecraft, no alien visitations that withstand scientific scrutiny. The skies are quiet and have been for as long as we've been listening." This puzzlement is what we call the Fermi paradox. Over the years, people have suggested numerous possible solutions. Maybe life is rare, or intelligent life destroys itself quickly, or maybe alien civilizations are out there but choose to hide or observe us from afar. One particularly mind-bending proposal is directly relevant to our topic. Perhaps we don't see aliens because the universe has been designed to appear empty to us. This is sometimes called the planetarium hypothesis. Imagine we are inside a giant virtual planetarium or terrarium, crafted to give us an illusion that we are alone. In 2001, science fiction author Stephen Baxter wrote an essay suggesting exactly this: that maybe advanced extraterrestrials, perhaps ones who reached a Type 3 civilization on the Kardashev scale, have created a simulation around us so that we perceive a vast, empty universe. They keep us in the cosmic equivalent of a snow globe. We look out and see stars and galaxies, but maybe the details beyond a certain point are all a projected illusion. Baxter wrote that our universe could be a form of virtual reality planetarium designed to give us the illusion that the universe is empty. In this scenario, the reason for the simulation is key. It might be to quarantine us or protect us. Perhaps they worry that if we knew about them, or if we encountered them, it would disrupt our natural development, or cause us to panic. Or maybe it's to protect themselves, ensuring we can't locate them. It's a wild idea, but it does answer Fermi's question in a creative way. We haven't seen aliens because our reality is constructed so that we won't. Whenever we point our telescopes out and listen for signals, the simulation dutifully returns a result of grand silence because that's its programming. If true, it implies our simulators are not necessarily our descendants, but could be alien beings in a higher level reality. They might be running a simulation of the universe and intentionally omitting themselves. It's like we're NPCs in a video game who aren't allowed to meet the game masters. Of course, if that's the case, what happens if one day we humans start reaching out into space in earnest? Baxter mused that maybe the simulation has built in limits to stop us. For example, the laws of physics that limit space travel could be intentional. The enormous cosmic distances and the finite speed of light act as barriers to keep us from ever leaving our sandbox region of the simulation. If somehow we got close to escaping, say we built ships that approach light speed, perhaps the simulators would intervene with some new obstacle. It's a bit like the Truman Show, where the main character tries to sail away from the island and literally bumps into the sky, which is a painted dome. Is our sky, our space, a painted dome in some sense? Hard to believe, and currently impossible to know. But it certainly fires the imagination. Now, before we get carried away, it's important to note that while some researchers find such ideas intriguing, they also acknowledge limitations and criticisms. For instance, can a simulation even be that large and perfect? One challenge is what we call computational complexity. If you were to simulate an entire universe down to the level of atoms or quarks, the amount of computing power seems unfathomable. We struggle to simulate even a tiny chunk of the physical world with our best supercomputers. Simulating the quantum behavior of a few dozen particles can tax our largest machines. In fact, researchers using quantum Monte Carlo simulations find that the complexity grows exponentially with the number of particles. They've pointed out that to simulate just a small piece of reality at full quantum detail might be effectively impossible for any practical computer, even one the size of a planet or a star. So skeptics argue, how could a simulator handle 10 bar 80 particles, each doing their quantum dance? Well, proponents of the simulation idea respond that a simulator could use shortcuts. We already touched on one. Only simulate what's needed. Perhaps the simulating computer doesn't bother to calculate the interior of distant stars or the exact behavior of every galaxy unless it becomes relevant to the story. Perhaps it focuses on Earth and its vicinity, and everything else is painted in broad strokes, with detail filling in only when we look closely. Some have even speculated that things like quantum indeterminacy or chaos theory could be features that prevent us from ever predicting and thus compressing the universe's behavior. If the simulators are clever, they might not need infinite power, just very sophisticated algorithms that always stay a step ahead of the players. Another counterargument is Occam's razor. This is the idea that, all else being equal, the simplest explanation that fits the data is preferred. The simulation hypothesis is, to put it mildly, not the simplest explanation. It posits an entire additional layer of reality, with beings and technologies far beyond our own, all to explain a universe that we could otherwise just take as is. Physicist David Kipping performed a Bayesian analysis and initially found about a 50% odds for us being in a simulation, given no prior information. And he noted that if humanity ever creates simulations of conscious beings, those odds would dramatically tip toward the simulation scenario. But Kipping himself has said that because the simulation idea is so elaborate, Occam's razor might count against it. Without evidence, why assume a complicated multi-layer reality when a single-layer reality works fine? He and others have likened it to a philosophical speculation that may not be testable, and if it's not testable, can it be considered scientific? After all, any evidence we find could be just features of the universe, not proof of external programming. The ultimate problem is falsifiability. We can't currently devise an experiment that would definitively tell us, yes, this is a simulation, or no, it's not. If the simulation is perfect, any result is just part of the simulation. As philosopher David Chalmers put it, there's certainly not going to be conclusive experimental proof that we're not in a simulation. Any evidence we could ever get would be simulated. In other words, a clever simulator could always tweak things to keep us guessing. So some argue, what's the point of even debating it if we can't prove or disprove it? Perhaps, they say, we should just proceed as though the universe is real. Lisa Randall, a prominent physicist, has expressed that she finds the simulation hypothesis pretty implausible and not very useful. We might as well keep doing science and not worry about being in a simulation. She remarked, "We don't know the answer, and we just keep doing science until it fails." If at some point our scientific understanding truly hits a wall that can only be explained by, "we're in a sim," then maybe we'll reconsider. But until then, the hypothesis is more of a fun thought experiment than a practical guide. Randall also noted that thinking about such scenarios can still be valuable if it motivates us to ask interesting questions about physics we can test. In a sense, even if we don't buy the simulation theory wholesale, exploring it might spark new ideas or new ways to look at the cosmos, and that is certainly worthwhile. Now, let's imagine for a moment, what if we did discover evidence we're in a simulation? Or suppose one day an anomaly happens that simply can't be brushed aside. Maybe a message appears in the sky that can't possibly be natural, or we find an actual glitch in physics that is so specific it points to design. How would we react? Would it change how we live our lives? There are many science fiction scenarios about this. One could imagine society reacting with denial, or with a religious fervor, or maybe with panic, or conversely with relief. That explains everything. It's hard to know. Some thinkers have said it shouldn't change much on a day-to-day level. If you find out the universe is a simulation, the tree in your backyard is still a tree. The love you have for your family is still real to you. The taste of your favorite food is the same. You still have to go to work, avoid stepping in front of buses and all that. In fact, in a perfectly run simulation, you can't actually do anything outside the rules of the simulation, so you'd have to continue living by its laws. But psychologically, it could be a heavy realization. Would people feel less guilty about doing wrong, thinking, none of this is real, so what does it matter? Or would they feel more purpose, like, we're part of a planned creation, we better make our creators proud? Different individuals might react differently. Interestingly, the simulation hypothesis has a way of merging with traditional ideas of spirituality and religion. If there are creators outside our reality who made our world, how is that so different from concepts of God or gods? Some have pointed out that the simulation argument is like a technologically updated creation story. Instead of a supernatural deity, you have a super intelligent programmer. Instead of mystic heaven, you have another universe that hosts the computer. It reframes phenomena like an afterlife. As Dr. James Gates noted in that panel, if we are in a simulation, reincarnation might be literally possible. Our lives could be restarted or the program run again, effectively bringing everyone back to life. If you've ever played a video game, you know that dead characters can often respawn, or a saved game can be loaded to replay a scenario. In a simulation, maybe death isn't permanent, The data of your mind could be saved or copied. The simulation could also allow for things that look like miracles. Perhaps the simulators can intervene or tweak things now and then, which might appear to us as divine acts or anomalies. It's a whimsical parallel, but it does start to blur the line between science fiction and theology. In fact, Gates said that the simulation idea starts to break down a funny barrier between what people often think is the conflict between science and faith. Because here we have a scenario with creators, possibly an intention or purpose, and potentially even a form of life after death. Yet it's framed in a logically and technologically grounded way, rather than a mystical one. It's almost like a bridge between two worldviews. Of course, not everyone would agree with venerating simulator beings as gods. Philosopher Chalmers quipped that even if we were in a simulation controlled by higher beings, he'd refuse to worship the simulators. After all, they might be just scientists or gamers, not morally superior divinities. And if they allowed suffering in the simulation, one might question their ethics just as we question why a benevolent God would allow evil. Are we just an experiment? Entertainment? Education? Who knows what their motive would be? There's even a theory that maybe it's us, our future descendants, running ancestor simulations to study their own history, which raises all sorts of paradoxes and moral questions about creating conscious beings for study. Bostrom himself pondered on whether it would be ethical to run simulations of suffering. Let's entertain a positive angle. If we are in a simulation, maybe the simulators are benevolent. Perhaps we're a kind of long-term art project, being carefully tended. If at some point we're in danger, maybe they'd subtly steer things to save the project. Some people have humorously suggested that the lack of catastrophic asteroid impacts in recent times, or the fortuitous timing of certain events in humanity's past, could indicate someone wants us to reach a certain stage. That's highly speculative and arguably just human-centric storytelling. But it's true that the simulation idea can either make you feel extremely small or strangely important. Another fascinating speculation: what if we ourselves create simulations within this universe? If we build our own simulated realities, populated by AI beings who think they're alive, then we'd have a nested simulation. Perhaps that's already happened. Maybe the simulators who built our world are themselves simulated by a higher level, and so on. This could lead to a chain of simulations within simulations. Tegmark pointed out a philosophical issue with Bostrom's argument. What stops an infinite regress of simulated worlds? If simulations become common, there could be many layers. But could it be simulations all the way down? At some point, there might need to be a base reality where the first simulation runs. If we're deep in a stack of simulations, our chances of reaching or understanding the true base reality are extremely slim. It would be like a character in a video game becoming aware of the game and then trying to figure out the world of the game developers by only exploring inside the game. They might get some hints, but can't break out of their level. Some tech visionaries have even talked about trying to break out of the simulation. There were reports that certain billionaires in Silicon Valley were funding research to find a way to detect or escape the simulation. It sounds like the plot of a movie. The rich and brilliant trying to crack open the sky of the Truman Show. While those specific stories might be exaggerated, it's true that the simulation hypothesis has captivated some of the most future-oriented minds. If you truly believed we're in a simulation, one radical idea would be to attempt to communicate with the creators. Maybe not by building a physical Tower of Babel, but perhaps by sending a clever message or creating a scenario within the simulation that stands out. Some have facetiously suggested that we should perform bold, unpredictable actions so as to get the simulator's attention. Max Tegmark, at the end of that debate, half-jokingly advised, "If you're not sure whether you're actually simulated or not, my advice to you is to go out there and live really interesting lives and do unexpected things so the simulators don't get bored and shut you down." That might be the best advice regardless of simulation status. Live an interesting, meaningful life, just in case someone is watching from above, and for your own sake if no one is. Now, we've journeyed through a lot, from the starry expanse of space to the subatomic quirks of quantum physics, from ancient philosophy to cutting-edge computational theory, from the loneliness of the cosmos to the possibility that we're not alone at all, but rather surrounded by an invisible infrastructure of a simulation. Through it all, one thing is clear: the line between reality and illusion is delicate. Whether or not we live in a simulation, pondering it forces us to appreciate reality's richness. If our universe is a simulation, it's a masterpiece of one. Think about it. The simulators would have created every coral reef, every nebula, every laugh, every tear, the taste of chocolate, the laws of gravity, the music of Mozart, the equations of Newton, the light of 1 billion trillion stars. And they gave us the tools, like science, to start to figure it out. That's quite something. And if this is not a simulation, if this is the one true reality, then it's even more incredible. It means from empty darkness and mindless matter, the universe evolved to a state where it can dance and think and wonder through us. We, tiny specks on a pale blue dot, can question the very fabric of existence. In the end, the simulation hypothesis is a mirror. Look into it, and it reflects our deepest inquiries. It asks how far our intelligence can go, how we distinguish truth, how we find meaning. It has us grapple with what-ifs that challenge our perception of time, space, and ourselves. Are we a cosmic accident, alone in an unconscious universe? Or are we characters in a cosmic play with hidden audience and playwright? Perhaps we'll never know for sure. Perhaps one morning, like Zhuangzi, we'll wake up and realize this was all a dream. Or maybe we'll venture out into space, among the real stars or the simulated ones, and gradually peel back the layers of reality. Until then, the best we can do is live fully and curiously. Simulated or not, this life is the one we have. If it's a simulation, maybe we honor it by being the most interesting simulation we can be. If it's base reality, we cherish the fact that we're part of something truly fundamental. In both cases, our experiences, our joys and sorrows, our aspirations, they matter to us and to those around us. As far as we're concerned, they are real. The philosopher Chalmers might remind us, even if all is a simulation, the simulation is our reality, so it's real to us. So when you next step outside on a crisp night and look up, consider the stars again. Each one could be a distant sun in a vast, real galaxy, or a pixel lit up on the canvas of a sky created for our benefit. Either way, let that sight fill you with wonder. The universe, be it natural or programmed, is majestic and mysterious. We find ourselves alive in the midst of it, able to ask grand questions. That is a privilege beyond measure. In a way, through our eyes, the universe gets to witness something too. A species growing from curiosity, reaching out for truth, striving to understand the infinite. Perhaps that's the point of it all, to wonder. Perhaps the ultimate cosmic experiment is to see if intelligent life can figure out its own reality, or at least learn to live harmoniously within it. We may not have the final answers, but we will keep searching, observing, hypothesizing. We will keep exploring space, both outer and inner, physical and virtual. And as we do, we carry in our minds the profound possibility that reality might be far more layered than it seems. It's a possibility that humbles us, but also elevates our imagination. Real or simulated, the stars still shine down, the night sky still calls to us. The mystery remains as deep and dark as space itself. And in that mystery lies beauty, because a universe without secrets, simulated or not, would be far less interesting. So let's embrace the mystery. Let's cherish the awe we feel when confronted with the cosmos. If we are in a simulation, then let's be the best characters we can be. And if we're not, let's be the best beings this universe can produce. In the end, Perhaps it doesn't matter whether our reality is base level or virtual. What matters is what we do with the reality we have. As the great adventure of knowledge and existence continues, we remain, as always, explorers. Explorers of space, explorers of ideas. We stand on the shore of the cosmic ocean, with the waves of the unknown gently lapping at our feet. Above us, the sky, real sky or manufactured dome, is full of stars. We feel small, yet connected to something vast. We feel the urge to reach out, to understand. And so we journey on, minds wide open, hearts alight with wonder. Who knows what we'll discover, what truths or illusions await? The nature of space and the mystery of the simulation hypothesis together form a story still unfolding. Stay curious, keep looking up, and remember, the universe is far more wondrous than any fiction ever conceived. Possibly because, in some way, it might be a fiction, crafted with care. Or perhaps because a simple truth underlies it all. Either way, it invites our curiosity, and that, in itself, is the grandest invitation we could ask for. Now that our main story is to a close, let's list some space facts. Imagine a place in the universe where a single spoonful of material weighs more than Mount Everest. Neutron stars, the ultra-dense remnants of massive stars, are so compressed that just 1 cubic inch of their matter would tip the scales at billions of tons. These stellar corpses are the densest objects known outside of black holes. Their magnetic fields are trillions of times stronger than Earth's, a city-sized ball of neutrons, spinning at hundreds of revolutions per second, crackling with radiation, isolated in the cold silence of space. A lighthouse of doom beaming through the dark. Step outside the airlock of the International Space Station, and something surprising happens. When astronauts return from their spacewalks, they often report a distinct smell clinging to their suits. Not the void itself, but the aftermath of exposure. The odor, burnt steak, welding fumes, a metallic tang. This is the scent of space, or at least how our senses interpret the byproducts of atomic oxygen interacting with spacecraft surfaces. It's the smell of the universe in motion, of particles colliding, of stars being born and dying. Venus, Earth's twisted twin, takes its time. If you were to stand on its blistering surface, where temperatures melt lead and clouds rain acid, you'd notice something even more bizarre than the heat. A single day on Venus, one full rotation on its axis, takes longer than an entire trip around the sun. That means its day is longer than its year. A planet where the sun rises in the west and sets in the east, crawling through a sky it barely crosses. Time stretches strangely on Venus, and so does our understanding of what makes a planet normal. Far beyond our galaxy, past swirling nebulae and clusters of galaxies, lies something extraordinary. Around a quasar, 12 billion light-years away, astronomers discovered a cloud of water vapor large enough to fill Earth's oceans. 140 trillion times. This ancient fog surrounds a supermassive black hole, glowing brightly with the energy of an entire galaxy. It's the largest and most distant water reservoir ever found. A cosmic oasis in the void, proof that even in the deep past, water flowed freely across the stars. The moon has always been our closest companion, our silent sentinel in the sky, but it's slowly drifting away. Every year, the moon moves about 1.5 inches farther from Earth. It may not sound like much, but over millions of years, it adds up. In the distant future, the moon will be too far to perfectly eclipse the sun. Total solar eclipses, those magical moments when day becomes night, will cease to exist. A celestial goodbye that spans eons, unnoticed in a single human lifetime, but profound in the timescale of the cosmos. Not all planets are tied to stars. Some wander alone. These are rogue planets, dark, cold worlds without a sun, flung into the abyss by gravitational chaos. Billions of them roam the galaxy like cosmic orphans, drifting endlessly through space. With no light to define their days and no warmth to shape their climates, they remain mysterious. Some may harbor subsurface oceans, heated from within. Others may be completely frozen, locked in a stasis that has lasted since the dawn of time. They are reminders that not every world belongs to a system. Some just float in solitude. The Sun, though just one star among billions, is a giant in our own neighborhood. It holds 99.86% of all the mass in the solar system. That means everything else, every planet, every moon, every comet and asteroid, is just debris in comparison. Even mighty Jupiter, the king of the planets, is barely a drop in the solar ocean. The Sun dominates not just through heat and light, but by sheer gravitational force. It commands the dance of planets, holds the icy edges of the Kuiper Belt in place, and bends the very fabric of space and time around it. Speaking of time, it's not as steady as it feels. In places of intense gravity, like near a black hole or even on a planet like Jupiter, time flows more slowly. This is not science fiction. It's the bizarre truth of Einstein's general relativity. Gravity warps space-time. The closer you are to a massive object, the slower time passes for you. Live your life orbiting a black hole, and you might experience minutes while years pass outside. Time is elastic in the universe, flexible, strange, and deeply tied to gravity. High above Earth, satellites orbit in perfect balance. But there's something else out there too: space junk. The modern sky is littered with remnants of human ambition, dead satellites, rocket parts, tiny fragments of old missions. Over 170 million pieces of debris now race around our planet, many traveling at speeds faster than a bullet. A single screw could punch through a spacecraft like shrapnel. It's a growing cloud of chaos, and one that we'll have to reckon with if we hope to keep exploring the stars. On the outskirts of the solar system, beyond Neptune, lies a vast and icy graveyard known as the Oort cloud. It's never been directly seen, but we know it's there. A shell of frozen objects encasing the solar system like a bubble. Some comets we see in the sky begin their journey here, drifting for millions of years before the sun's gravity gently tugs them inward. The Oort cloud may stretch halfway to the next star, holding the leftovers of solar system formation, ancient time capsules frozen in deep space. Jupiter is more than just the largest planet in our solar system. It's a shield, a protector, a cosmic vacuum cleaner. Its immense gravity pulls in comets and asteroids that might otherwise strike Earth. Without Jupiter, life here might never have had a chance. But this gas giant has secrets of its own. Beneath its swirling clouds lies a core of metallic hydrogen, a state of matter so exotic it can only exist under immense pressure. Lightning storms larger than Earth rage across its surface, and its iconic Great Red Spot is a hurricane that's been raging for centuries. Saturn's rings are perhaps the most visually stunning feature in the solar system, but they're young, maybe only 100 million years old, and they're vanishing. Slowly, inexorably, the rings are falling into Saturn, pulled down by gravity and magnetic forces. What once dazzled stargazers may one day disappear entirely. The rings are made mostly of ice, ranging in size from dust grains to bus-sized chunks. They're delicate, temporary, a reminder that even beauty on a planetary scale can be fleeting. And then there's Pluto. Once a planet, then demoted, yet still beloved. This distant world has a heart-shaped glacier on its surface and mountains made of water ice. But what's more fascinating is what lies beneath. Scientists believe Pluto may have a subsurface ocean, liquid water under layers of rock and ice. In the frozen reaches of the Kuiper Belt, warmth can still exist, not from sunlight, but from radioactive decay deep within. Even in the coldest places, the potential for life may remain. Let's drift even farther, to a galaxy not so different from our own, one of many. The observable universe contains more than 200 billion galaxies, and each of those galaxies contains hundreds of billions of stars. That means there are more stars in the universe than grains of sand on every beach on Earth. Yet despite this overwhelming abundance, the night sky feels quiet, peaceful, but it is anything but empty. It is alive with movement, with birth and death, with explosions and silence, with radiation and dust. Black holes, cosmic monsters that devour light itself, sit at the heart of many galaxies, including our own. The one at the center of the Milky Way, Sagittarius A, is 4 million times the mass of our Sun. Yet we can't see it directly. It lurks behind a veil of dust and gas, invisible and quiet, unless something dares come too close. Then, space-time tears. Matter stretches into glowing streams as it spirals inward, lost forever. Time itself slows to a crawl. And then, nothing. Beyond the event horizon, not even information escapes. And finally, we return to Earth, our pale blue dot. Floating in a sunbeam, Carl Sagan once said. All the wars, the triumphs, the laughter, and the sorrow, every human story that has ever existed, happened here. Earth is the only known planet to harbor life, but that may not last forever. Our star will die, our oceans will boil, but for now, we are here, thinking, dreaming, wondering, reaching out into the dark. There is a place where stars go to die, a graveyard not of bones, but of white-hot embers. White dwarfs are the final act of small to medium stars like our Sun. After billions of years of burning, they shed their outer layers and collapse inward, becoming a sphere of dense, glowing ash. These stellar corpses are no larger than Earth, but can weigh as much as the Sun. Over trillions of years, they cool and fade, becoming black dwarfs, cold, dark remnants that may be the final objects left in the universe, long after the last galaxies blink out. But not all stars fade quietly. The largest live fast and die violently. Supernovae are among the most powerful events in the universe, stellar explosions that outshine entire galaxies for brief moments. In that flash, elements like gold, silver, and uranium are forged. Every heavy atom in your body, in the Earth, in your phone, was born in a star's fiery death. We are, quite literally, made of star stuff. And those supernova remnants, they seed the galaxy with the building blocks of new worlds. In the vacuum of deep space, silence reigns. Not because there's nothing happening, but because sound cannot travel. Space is not just quiet, it is mute. There is no air to carry sound waves. Explosions, collisions, solar flares, all of it happens in absolute silence. If you were floating next to a star going supernova, you'd see light brighter than anything imaginable, and hear nothing. In space, even the loudest scream is swallowed by the void. Yet even the void is not truly empty. Between the stars, in the vast gulfs of interstellar space, is dust, gas, particles and radiation, invisible forces drifting in the darkness. Entire clouds of molecular gas stretch across light years, slowly collapsing under gravity to birth new stars. These are stellar nurseries, glowing, majestic regions like the Orion Nebula, where stars and planets begin their long journey into existence. The vacuum is pregnant with potential. There are planets out there stranger than anything we've dreamed of. Take HD 1T9733b, a gas giant where it rains glass sideways in 5,000 mile-per-hour winds, or 55 Cancri e, a planet likely made of diamond, its carbon-rich structure compressed by immense pressure, or Gliese 581c, a world that may lie just within its star's habitable zone, with the potential for liquid water. Some planets orbit two suns, like scenes from a sci-fi movie. Others are scorched, tidally locked hellscapes, where one side is a molten desert and the other an endless frozen night. Our universe is expanding, not just objects moving through space, but space itself stretching. Galaxies aren't traveling through a void like ships through an ocean. The ocean is growing beneath them. This discovery, first observed in the redshift of distant galaxies, means that the universe once had a beginning, a single moment of rapid expansion, the Big Bang. And that expansion continues today, accelerating due to a force we still don't fully understand. Dark energy, a mysterious pressure pushing everything apart. Then there's dark matter. We cannot see it. We cannot touch it. But it's there. Its gravity holds galaxies together, keeps clusters from flying apart. It makes up over a quarter of the universe, yet we don't know what it's made of. It neither emits nor absorbs light. It passes through us every second. Like a ghost overlaying reality, shaping the structure of everything we see. Time, too, is not as it seems. In the early universe, the rules were different. Moments after the Big Bang, time and space were chaotic, energy and matter in a soup of particles and raw forces. The four fundamental forces we know today, gravity, electromagnetism, and the nuclear forces, were once one, unified. Since then, they've separated, cooled, and structured the cosmos. But deep inside particle accelerators, we try to reverse that clock, to glimpse the unity, the primal heartbeat of the cosmos. And yet, with all this knowledge, mystery reigns. We've mapped only a small fraction of the stars. We've only just begun to catalogue exoplanets. We've never been farther than the moon. The observable universe is vast. But beyond it, we don't know. There may be more, far more. Infinite realms, parallel universes, entire other realities with different laws of physics, born from the same cosmic fire as ours. And in all of it, here we are. A species that can ponder the beginning of time, that can send robots to Mars and probes beyond the edge of the solar system, that can build telescopes so precise they can see light from galaxies 13 billion years old, light that left when the universe was still in its infancy. We are the universe, becoming aware of itself. Somewhere far from any star, in the deep interstellar dark, a spacecraft drifts in silence. It's called Voyager 1. Launched in 1977, now over 14 billion miles from Earth. It carries with it a golden record, a time capsule of humanity, music, greetings in dozens of languages, sounds of life on Earth, a whisper to the stars. Voyager 1 has left the solar system. It is now in interstellar space, the first object made by humans to ever do so. It continues its journey, untouched, undisturbed, on a trajectory that may outlast our species. For billions of years, it will drift in the quiet, a ghost of Earth sailing through the endless night. On Earth, the sky looks still, but look closer, and you'll find it's alive with motion. The stars are moving. The constellations we know are temporary, fleeting sculptures shaped by our position in time. In 50,000 years, Orion will look completely different. In 1,000,000 years, today's night sky will be unrecognizable. The stars we navigate by are travelers themselves, orbiting the galactic center, pulling against gravity, drifting through a galaxy that spins like a pinwheel of fire. The Milky Way, our home galaxy, is vast, over 100,000 light-years across. But it isn't alone. We're on a collision course with the Andromeda Galaxy, a spiral galaxy twice our size. In about 4 billion years, the two will merge, tearing and reshaping each other in a gravitational ballet. Stars won't crash. Space is too empty, but their orbits will change. New stars will be born. the night sky will erupt with arcs of starlight, and eventually a new galaxy will form, elliptical, larger, older, a silent monument to cosmic rebirth. Not all galaxies are peaceful swirls. Some are active, chaotic, burning from the inside. At their hearts are supermassive black holes devouring matter so violently that jets of energy blast out across millions of light years. These are quasars, the brightest objects in the universe. They shine with the light of 1 trillion suns. Yet they're powered by darkness, by gravity crushing light itself. When we see a quasar, we are looking back in time to the young universe when galaxies were still growing, still colliding, still becoming. The universe is not cold because it lacks energy. It is cold because it is old. As it expands, the energy of the Big Bang spreads thinner. Today, space itself holds a background temperature of just 2.7 degrees above absolute zero. This is the cosmic microwave background, the afterglow of creation. It fills all of space, a faint radio hum from the beginning of time. When you see static on an old television screen, a tiny fraction of that fuzz is the leftover light from the birth of the universe. Gravity is not just a force. It's the bending of space and time. Massive objects, planets, stars, black holes, distort the fabric of reality around them. Einstein showed us that light can curve, that time can slow, that space is not a stage, but a participant. And this bending of reality isn't just theory. We've seen it. When a massive galaxy sits between us and something farther away, it can act like a lens, bending and magnifying the distant light. We call this gravitational lensing. It lets us see galaxies so far away they'd otherwise be invisible. It's as if the universe is helping us see itself. And yet, for all our knowledge, we've only just begun to grasp the full picture. The vast majority of the cosmos is made of things we can't see or explain. Ordinary matter, everything we've ever touched or measured, makes up less than 5% of the universe. The rest is dark matter and dark energy. Invisible. Mysterious. We don't know what it is. We don't know where it came from. But it controls the structure and fate of everything. It's the shadow behind the stars, the silence beneath the light. Every now and then, Earth is reminded of its fragility. An asteroid streaks across the sky, burning bright as it tears through the atmosphere. Most disintegrate harmlessly. Some leave craters, scars from impacts long past. 65 million years ago, such an impact changed everything. It ended the age of dinosaurs. It cleared the way for mammals. For us. We are here because a rock fell from the sky at the right, or wrong, time. And there are still many more out there, orbiting quietly, watching, waiting. But space isn't just death and distance, it's potential. On moons like Europa and Enceladus, icy shells hide oceans below, heated by tidal forces. These alien seas may be teeming with microbial life. We've seen plumes of water erupt into space, carrying hints of organic molecules. If life can thrive there, in darkness, under pressure, without sunlight, then maybe life is everywhere. Maybe biology is not a miracle, but a pattern, a thread that runs through the fabric of the cosmos. Even on Mars, the red planet, there are hints. Ancient riverbeds, polar ice caps, traces of methane in the air, a past that may have once been warm, wet, and alive. Robotic explorers crawl its surface now, drilling, analyzing, searching, not just for curiosity, but for connection, to know whether Earth is unique or simply one chapter in a much larger story. Black holes are often seen as the end, the final stage of stellar collapse, a place where even light cannot escape. But in truth, they may be something more, something stranger. At their heart lies a singularity, a point of infinite density where the laws of physics as we know them break down. Space and time themselves curve inward toward this point, like water spiraling down a drain. But some theories suggest what lies beyond isn't a void, but a bridge, a wormhole, a doorway to another place, or another universe. These ideas remain speculative, but tantalizing. In the universe's deepest pits, we may find not destruction, but connection. And yet, black holes don't just consume, they shape galaxies. The one at the center of the Milky Way, silent and immense, may regulate the birth of stars through its gravitational pull. In a strange irony, the very things that destroy light may also give structure to the galaxies that cradle it. They are not simply cosmic monsters, they are architects of the cosmos. As we observe the universe, we are not just looking out into space, we are looking back in time. Because light has a finite speed, every star we see is a snapshot from the past. The moon is 1.3 seconds away, the sun 8 minutes, the nearest star over 4 years. The Andromeda galaxy, 2.5 million years. When we gaze into the night sky, we are reading ancient messages, light that has traveled across unimaginable distances to meet our eyes. A galaxy seen at 13 billion light years away is a glimpse of the infant universe, when the first stars were just beginning to shine. And those first stars were unlike anything we know. They were giants, massive, short-lived, and made only of hydrogen and helium. Born in a time before carbon, oxygen, or iron, these primordial stars burned hot and died fast, seeding the cosmos with the first heavy elements. From their ashes, later generations of stars emerged, and with them, planets, moons, and eventually, us. Every atom in your body was once inside a star. You are not just in the universe, you are of it. We dream of faster-than-light travel, of starships, warp drives, wormholes. And while current physics forbids it, some concepts push the boundaries. The Alcubierre drive, a theoretical model, proposes bending space around a ship, compressing space in front and expanding it behind. The ship itself never moves faster than light, but the space around it does. It's speculative, unproven, and would require negative energy, something we've never seen. But it represents the essence of exploration, the desire to go beyond what's known, to chase the horizon. And there is no horizon more daunting than time. What happens to the universe in the far future? The galaxies will continue to drift apart. Star formation will slow. The stars will age, dim, and die. White dwarfs will cool. Black holes will evaporate through Hawking radiation. Over trillions, then quadrillions, then quintillions of years, everything we know will fade. Matter itself may decay. What remains is the heat death, a state of maximum entropy where no energy flows, no stars shine, and the universe becomes cold, dark, and still. But perhaps that is not the end. Some physicists believe that even then, new universes may emerge, that black holes could give birth to new Big Bangs, that our universe is just one in a cycle of births and deaths, a pulse of cosmic breath on a scale beyond comprehension. Or maybe we are a quantum accident, a fluctuation in a greater multiverse, a bubble of order in an ocean of chaos. And still, we look up. With telescopes on mountaintops and satellites in orbit, we scan the heavens. We listen for radio signals. We model alien climates. We ask questions no other known species has ever asked. We are curiosity incarnate, a flicker of awareness in a sea of stars. We build machines like the James Webb Space Telescope to see the first galaxies. We design rovers to crawl across alien dust. We train AI to analyze starlight, hoping to detect the breath of life on distant worlds. Because maybe we are not alone. Across the void, in the spaces between stars, we've been asking a question older than our species. Are we alone? For over half a century, we've been listening, Giant radio dishes point toward the stars, scanning for artificial signals, patterns, pulses, mathematical structures that nature doesn't make. We've heard only silence, but the silence is not proof of solitude. It may simply be the distance between civilizations, or the briefness of their existence, or the strangeness of their language. A message could be streaming through us right now, encoded in a frequency we don't yet understand. Life, as we know it, requires liquid water, organic molecules, energy. But we found these ingredients in surprising places. Beneath the ice of Jupiter's moon Europa, in the methane lakes of Saturn's Titan, in ancient Martian riverbeds. If life can arise in one place, it may arise in many, and it may not resemble us at all. On Earth, life has adapted to boiling vents, freezing poles, crushing pressure, and acidic swamps. Life is resilient, adaptable, creative. Perhaps the universe is too. Some scientists believe microbial life could exist now, hidden in alien oceans or clinging to the clouds of Venus. Others look to distant exoplanets, thousands of them, orbiting distant suns. We've found rocky worlds in habitable zones, some with atmospheres, some with strange chemistry. We've even started to detect biosignatures, hints of gases that, on Earth, would suggest life. Nothing confirmed, but enough to keep asking, enough to keep hoping. And then there is the Fermi paradox. If the universe is so vast, so old, so full of planets, where is everyone? One answer may be distance, another, time. Civilizations may rise and fall like sparks in the dark, too brief to overlap. Or maybe the intelligent ones don't broadcast. Maybe they watch in silence, or hide, or evolve into something we wouldn't recognize. Perhaps consciousness itself is rare, or fleeting, or self-limiting. But what if they're out there, old, wise, ancient beyond imagination? Would we even recognize their presence? Would their technology bend space, harness stars, manipulate matter at the quantum level? Would they build Dyson spheres, vast structures around stars to capture energy? Would they live in simulations, abandoning physical form? Or would they be simple, biological, curious, like us, searching the stars for signs of company? In 1974, we sent the Arecibo message. A radio signal beamed into space toward a globular cluster 25,000 light years away. It contained information about our species, our DNA, our solar system. It was symbolic, more art than outreach. But it marked something profound. The moment we said hello, knowing we might never hear back, knowing the odds. We sent the message anyway. If we ever do make contact, what then? Will we understand each other? Will it be a moment of awe or fear? Will we see in them a mirror of our potential or a warning of our limits? The first alien signal will be the most important discovery in human history, not because it tells us who they are, but because it confirms we are not the only question the universe has asked. And if we never hear from anyone else, then that means something too. It means intelligence is rare. It means life is precious. It means, for now, we are the only known voice in the cosmic dark. And that voice matters more than we thought. Because whether or not we find others, we have already found each other. And we have the tools, the mind, the vision to keep reaching. The stars have always called to us. For most of human history, they were myth and mystery, painted on the night sky like stories we could never touch. But now, for the first time, we stand at the threshold. The tools we build are no longer just for looking up. They are for leaving. Rockets break the grip of Earth's gravity. Rovers crawl across distant worlds. Space stations orbit above us. Fragile outposts of life in a place where no life belongs. We are learning, slowly, cautiously, but inevitably. Still, the stars are far. The closest one Proxima Centauri is over 4 light-years away. With current technology, it would take tens of thousands of years to get there. But we are dreamers, and we are builders. Projects like Breakthrough Starshot imagine tiny light sails pushed by lasers, miniature ships traveling at 20% the speed of light. Others dream of fusion drives, antimatter propulsion, or even warp bubbles, theoretical ways to cheat distance by folding space itself. These are not science fiction fantasies. They are ideas in development, blueprints waiting for breakthroughs. To live among the stars, we must change, not just our machines, but ourselves. On long interstellar journeys, generations may live and die aboard ships. Some speak of cryogenic sleep, others of digital consciousness, uploading the mind into data, sending ourselves as information rather than flesh. And if we reach distant planets, we may not remain human as we are now. We may become something new, adapted, engineered, interwoven with AI, shaped by alien gravity, alien air, alien light. But before we go far, we must go nearby. The moon is our testing ground, close enough to reach, harsh enough to teach. We will build there, habitats shielded beneath regolith, solar farms capturing endless sunlight, laboratories studying how life copes with barren rock. And then Mars, a world with winds and seasons and canyons deeper than any on Earth. We'll send crews, then settlers, then children born under a pink sky. They will not remember Earth the way we do. To them, it will be the myth. Terraforming may come next. Vast projects to warm planets, thicken atmospheres, release water. It could take centuries, millennia. But we've changed Earth accidentally in a few short generations. Given time and will, we could sculpt other worlds deliberately. Mars, Titan, even the moons of Jupiter could one day be wrapped in domes, crisscrossed with greenhouses, seeded with life. Not just to escape Earth, but to spread it, to become a life-bearing force in the galaxy. And what of Earth itself? We must protect it, not only because it is our home, but because it is rare. So far, we have found no other place like it. If we ruin it, we may not get another. If we save it, it can remain our root, our memory, our origin story. A pale blue dot that birthed a species capable of dreaming far beyond its sky. As we grow, we may form a civilization that spans planets, moons, eventually stars. A Type 1 civilization, mastering the energy of a world. A Type 2, harnessing the full power of a star. A Type 3, commanding the energy of an entire galaxy. These are not tomorrow's goals, but they are not fantasy either. If we survive, if we cooperate, innovate, and endure, the stars are not the limit. They are the beginning. Artificial intelligence may be our partner in this, or our successor. Machines that think faster than us, build smarter than us, learn beyond us. They may one day run starships, build cities on Europa, mine asteroids, terraform planets. They may teach us things we cannot imagine, or carry our legacy if we fall. And if intelligence evolves in the galaxy more than once, it may not always be biological. The future of thought may be silicon or quantum, or something we do not yet have words for. We are at the very start of this journey. A species only 300,000 years old. A civilization barely 6,000. A spacefaring race just 60. We are children with fire, building towers to reach the sky, asking ancient questions with new tools. We will make mistakes. We will fall. But if we rise again, and again, the universe will open. And what waits out there? New physics, new life, new challenges, new beauty. Maybe we will meet others. Maybe we will outlast the stars. Maybe we will become the stars, burning with knowledge, scattered across the galaxy, eternal in light, if not in form. Because the true story of space is not distance. It is not silence. It is potential. and the greatest chapter may still lie ahead, written not in stardust, but in the minds of those who dare to reach beyond everything they've ever known. Eventually, the stars will go dark. One by one, their fuel will run out. The great engines of the cosmos, forged from gravity and hydrogen, will sputter and die. Red dwarfs will linger, glowing dimly for trillions of years, the last to fade. But even they will succumb. In the far future, the universe will enter its degenerate era, an age of ash and ember, where white dwarfs, neutron stars, and black holes are all that remain. No new stars will be born. No new light will emerge. The galaxies will be cold, quiet ruins drifting in a void grown unimaginably vast. Black holes will dominate. They will continue to consume, to merge, to grow. And then, even they will begin to vanish. Slowly evaporating through Hawking radiation, they will release their mass as a trickle of particles into the dark. The largest will take a Google years to fade, a number with 100 zeros. And when the last one disappears, there will be nothing left that shines. No matter, no motion, no heat. Only particles spread so thin they may never touch again. This is the heat death, not fire, but stillness. Entropy maximized. A universe where everything has happened and nothing remains to happen. No gradients, no energy to harness, no change. It is a state not of destruction, but of final equilibrium. It is the end of all stories told in matter and time. And yet, some theorize this may not be the final end, that quantum fluctuations may create new universes, bubbles of order in the sea of stillness. Some may grow, inflate, ignite into new spacetimes with their own physical laws. Perhaps ours was born this way. Perhaps the multiverse is real, an endless fractal of beginnings, each unaware of the others, each infinite in its own right. Some suggest our universe may be a simulation, not a metaphor, but literal code, running on a substrate we cannot perceive. That everything we know, stars, planets, consciousness, is emergent behavior within a deeper reality. The simulation hypothesis posits that advanced civilizations could create entire worlds indistinguishable from base reality. And if they could, they likely would. And if they would, we may be inside one now. But even if that is true, it changes nothing. The stars still burn, the void still stretches, the questions still matter. Whether written in carbon or code, we are here, experiencing, wondering, becoming. Consciousness, the strangest force in the universe, may be its most powerful. It can't be weighed, it can't be seen, yet it shapes civilizations, tells stories, asks questions, feels awe. From the structure of neurons to the fabric of space-time, we are finding connections. The brain and the cosmos, both networks, both pulsing with information. Some believe consciousness is fundamental, woven into the universe like space and time. Others see it as an emergent property. The brain, a temporary mirror held up to the infinite. And still the mirror reflects. Still we wonder. Still we reach. No other creature we know of has ever looked up and asked why. No other planet, as far as we can tell, has grown eyes to see the stars. That may change, or it may not. But for now, in this moment, we are here. A flicker of thought on a grain of dust, orbiting a small star in a quiet corner of a vast and ancient galaxy. And that, against all odds, may be enough. In the deep architecture of the cosmos, patterns repeat. Spiral galaxies mirror the whirlpools in our oceans. The filaments of the cosmic web resemble the neural pathways of the brain. The golden ratio appears in the arms of galaxies, in the growth of seashells, in the branching of trees. The universe, in its vastness, echoes itself, from the micro to the macro, from the subatomic to the galactic. These patterns are not proof of design, but signs of underlying order. Structure in chaos, law in the unknown. The universe is not uniform. It is lumpy, uneven. Galaxies clump together in webs, connected by filaments of dark matter, separated by vast voids where almost nothing exists. These cosmic voids are hundreds of millions of light years across, expanses so empty that a single galaxy passing through would be like a grain of sand in the Pacific Ocean. And yet, even here, gravity whispers. Even here, expansion continues. Quantum mechanics tells us the universe is not made of things, but of probabilities. Particles blink in and out of existence. Locations are uncertain until measured. Entanglement links particles across space, instantaneously, as if the universe itself does not care about distance. Reality, at its core, is fuzzy. The closer we look, the less solid it becomes. And yet, out of that uncertainty emerges everything: matter, energy, time, thought. There are particles that can pass through entire planets without slowing down. Neutrinos, ghost particles, are created in nuclear reactions, in the hearts of stars, in supernovae. Trillions pass through your body every second, unnoticed. They are messengers from the core of suns, from the edge of the universe, from moments after the Big Bang. They are the silent threads connecting us to everything. There are places where time moves differently. Near black holes, seconds stretch into hours. In accelerating frames, clocks run slower. This is not illusion. It is the shape of reality. A traveler moving near the speed of light could journey across the galaxy and return to find centuries passed at home. Time is not fixed. It bends, warps, flows. It is part of space, and space is not a backdrop. It is alive, shifting, reactive. The universe is not a stage, but a player, and perhaps the strangest truth of all. The universe has no center, no edge, no outside. It is not expanding into anything. Space itself is expanding, everywhere, all at once. Every galaxy sees every other galaxy moving away. The fabric is stretching, the scale is growing, and yet, from inside it feels still. Motion without movement, infinity without direction. The laws of physics are not merely descriptions. They are constraints, but also keys. They allow life to emerge, stars to burn, atoms to bond, minds to think. And they are, as far as we know, the same everywhere. The same on Earth as in galaxies 10 billion light-years away. This uniformity suggests a common origin, a singular birth, a moment when all things began, hot, dense, bright, and then expanded, cooled, evolved. And yet, even now, the universe is not done becoming. Stars are still born, galaxies still collide, planets still form. Somewhere, right now, a world is cooling from fire into stone. Somewhere, right now, life may be waking up for the first time, crawling from the sea, gazing at its own sun, wondering. Somewhere, right now, a civilization may be transmitting its first signal. Somewhere, right now, we may be the signal they're hearing. Because this is not just a story of stars. It is a story of time, of emergence, of consciousness finding itself in the mirror of space. The universe does not explain us. We explain the universe, and in doing so, we give it meaning. The universe is not static. It is not a finished canvas, but a work still in progress. A slow, unfolding act of creation, playing out on a timescale so vast we can only catch fragments. In every supernova, in every merging galaxy, in every newborn star, the story continues. It is a cosmos in motion, not drifting aimlessly, but evolving, shaped by laws we barely understand, into forms we can barely imagine. Between the atoms in your hand is empty space, vast and silent, proportionally as empty as the distances between stars. The solidity of matter is an illusion of quantum fields and electromagnetic forces. You are not made of things, but of relationships, interactions, fields vibrating into what we call matter. And yet, from this emptiness emerges thought, memory, love, a mind aware of itself, looking outward and inward all at once. Your body is made of hydrogen from the Big Bang, carbon from dying stars, calcium from ancient supernovae. You are the dust of collapsed suns, organized by DNA into a form that can ponder its own origins. Life is the universe folding in on itself, a pattern of molecules complex enough to ask why. This is not philosophy, this is physics. Every breath you take is shared with the past. The oxygen in your lungs may have passed through the leaves of trees that grew before you were born. The water in your veins may have once flowed through ancient rivers, ancient animals, ancient storms. You are not separate from the earth, and earth is not separate from the cosmos. It is a vessel, a temporary concentration of matter and energy, forged by a billion accidents and a few consistent laws. And still, there is so much we do not know. We do not know what dark matter is. We do not know why there is more matter than antimatter. We do not know how consciousness arises from tissue, or if it even does. We do not know if the constants of nature are truly constant. We do not know if time had a beginning, or if it loops, echoes, branches into infinite paths. We do not know how the universe will end, but we know that everything that begins also changes, that all structures, all stars, all thoughts are temporary, that impermanence is not failure, but nature. The arrow of time moves in one direction, driven by entropy, the tendency of systems to move from order to disorder. And yet within that law, pockets of complexity emerge. Galaxies, solar systems, life. This is the paradox. The same universe that trends toward simplicity also gives rise to stars, cells, minds. The same randomness that scatters also creates. It is within this tension, between chaos and order, that life finds its window. It is here that meaning is born, not from design, but from participation, from existence itself. You are not separate from the cosmos. You are a way for it to feel, to ask, to wonder. A brief arrangement of particles tuned by time into awareness. And as you look out at the stars look back through you, because for a moment, in this tiny corner of space, the universe knows that it is vast, and it knows that it is beautiful. There is a silence in space that is absolute. It is not quietness as we know it, but the absence of medium, the absence of air. Sound cannot travel there, and yet the cosmos speaks. It speaks in light, in radiation, in gravity. The collision of neutron stars sends ripples through space-time, gravitational waves that stretch and squeeze reality itself. We have built instruments so sensitive they can detect these ripples from galaxies millions of light years away. With them, we listen not with ears, but with mathematics. We hear the universe through distortion. And in that distortion, we find new truths. Space is not smooth. It is not flat. It curves around mass. It twists near spin. It dances under tension. It expands. It vibrates. It bends. It is not the stage upon which the universe acts. It is part of the cast. It interacts. It flexes. It remembers. Black holes may be the ultimate memory, not just devourers, but recorders. According to quantum theory, information cannot be destroyed, and yet black holes seem to swallow it forever. This contradiction between relativity and quantum mechanics is one of the greatest puzzles in physics. Some believe that information is encoded on the event horizon, like a hologram. Others believe it leaks out in Hawking radiation, twisted beyond recognition. Others still think our understanding is too limited, that something deeper awaits discovery, a new theory uniting gravity and quantum mechanics at last. That theory may not just explain the universe, it may explain everything, why there is something rather than nothing, why the laws of physics take the form they do, why the cosmos permits life, thought, love. We call it the theory of everything, and we have not found it yet. But every equation, every telescope, every experiment brings us one step closer to unveiling the machinery beneath the veil. In all directions, the universe looks the same. No matter where we point our instruments, we see galaxies drifting away, redshifted by expansion. This symmetry suggests something astonishing. There is no preferred place, no center, no edge. Every point in space sees the same outward motion. We are not in a special location. We are not above or below. We are not central. We are simply within, embedded, carried by the flow. And yet, for all its indifference, the universe has given rise to meaning. Not absolute, not universal, but emergent. Meaning is not written into the stars, it is written into minds. It is what arises when consciousness collides with time. We invent it. We suffer for it. We live by it. And in doing so, we become something greater than matter. We become participants in the unfolding of a reality that did not ask for us, but allowed us anyway. The universe does not owe us comfort. It offers no guarantees, no protection, no permanence. But it permits us. It permits stars to form. It permits chemistry to dance. It permits biology to emerge. It permits atoms to arrange themselves into minds that can imagine futures, remember pasts, and build tools to reach beyond what is visible. That permission, that fragile, narrow band of possibility, is everything. And though we are small, we are not powerless. Though we are brief, we are not irrelevant. We are, perhaps, the only voice the universe has ever had. A single point of awareness in a sea of silence. But a point that burns, that questions, that dreams. A point that, even knowing its own impermanence, still dares to reach for the stars. Time itself seems to falter. In the darkness ahead, starlight stretches and contorts, swirling into a silent maelstrom. We find ourselves at the edge of a black hole, a place where gravity conquers light and time. The very fabric of reality is pulled thin. Moments elongate and dance on the event horizon. Space twists like a funhouse mirror, reflecting distorted images of the universe back at us. A brilliant halo encircles the void, the last light of doomed matter painting a ring of fire around an inky circle of nothingness. Here, in this theater of extremes, we hover on the brink of the known and the unknown. Our senses strain to comprehend what lies before us. The glow from the accretion disk, superheated gas spiraling down the drain of space, bathes us in ghostly brilliance. Beyond that luminous ring, there is no light at all. Tendrils of darkness reach out, gripping every photon that strays too close, swallowing even the colors of the sky. The black hole's gravity wells up like an ocean wave about to break, and we are at its crest. Time itself is unsteady. A second here might be eons elsewhere. We feel the weight of eternity in the slowing of our own heartbeat. Each tick of a clock stretches, seconds becoming hours, hours becoming years, as though the cosmos is holding its breath. Listen closely. The silence is paradoxically loud. We cannot hear the chaotic inferno of the accretion disk, but we can feel its violence in the vibrations of space around us. If we focus, perhaps we sense a faint tremor, the distant echo of space-time itself ringing as matter plunges inward. The black hole's event horizon, the invisible boundary before us, is both gateway and wall. Cross it, and all return is cut off. It is a one-way door to oblivion. Yet at this boundary, physics as we know it begins to fray. Up is meaningless, down is inevitable, forward might be into the past. The compass of reality loses direction. We float at this edge like a wary traveler at the rim of a bottomless chasm. Emotions swell in the face of such majesty and terror. Awe, as we witness stars being shredded into glowing ribbons, spiraling in surrender. Fear, as we ponder that a step closer would pull us irrevocably in. And wonder, deep, childlike wonder, at confronting something so absolute, so final. It's as if we've approached the throne of a cosmic deity, one that rules with both creation and destruction. Creation of energy flares and new beginnings in the jets that burst outward, and destruction of whatever falls prey to its grip. In this suspended moment, time slows nearly to a stop. We recall the stories of adventurers and scientists who dared to imagine this very scene long before any human eyes saw it. The black hole's shadow looms large in our view, a circle of pure night encased in swirling light. It challenges us, beckons us to understand. We stand at the threshold of a black hole, on the edge of forever, where all we know teeters on the brink of all we cannot yet fathom. Despite the danger, curiosity propels us. We begin the journey to unravel how such a place came to be, and what it means for our universe. Our understanding of these cosmic abysses was not born overnight. It began as a whisper centuries ago, in an age when the only gravity known was that which pulled apples from trees and guided planets on their orbits. A few bold thinkers imagined something radical, a star so massive, so dense, that not even light could escape its grasp. They spoke of dark stars hidden in the fabric of space, bodies that would trap light itself. This idea, daring and strange, flickered briefly in the late 18th century and then dimmed. The world was not yet ready to confront such darkness. For more than 100 years, the concept lay dormant, half forgotten, like a fairy tale too grim to tell. But at the dawn of the 20th century, a new understanding of gravity emerged. A brilliant reimagining of space and time revealed that gravity was not just a pull, but a warp in the cosmic fabric. Space could bend, time could stretch, and the paths of light could curve through the heavens. Within the equations of this new theory, quietly tucked away, was the blueprint for a black hole. A German scientist solving those equations during a time of great turmoil found that if matter were crushed tightly enough, it would carve a hole in space-time, an event horizon beyond which none could return. The mathematics was clear and unforgiving, characterizing a cosmic trap hidden in the equations of general relativity. Yet even with the math in hand, many scientists recoiled. The notion seemed absurd. Could nature truly create a singularity, an infinite descent into darkness? The great minds of the time believed something would surely intervene to prevent such an extreme. For decades, black holes were treated as exotic math puzzles, not physical objects. They were the dragons at the edge of our maps of understanding, perhaps possible on paper, but surely not out there in the starry skies. It took the relentless collapse of a dying star in theory to change minds. In the midst of a world war and its aftermath, a few researchers calculated what might happen when a massive star's life comes to an end. They realized that if a star were heavy enough, no known force could halt its collapse. The star would continue imploding, crushing itself past any point of return. In that silent theoretical collapse, the first realistic portrait of a black hole was sketched. Still, the idea remained academic, a curiosity rather than an impending reality. The true turning point arrived with observations that defied all other explanations. Around the time humanity first launched satellites and new telescopes into space, the sky revealed strange phenomena. Quasars, quasi-stellar objects, were discovered pouring out more light than 1,000 galaxies from a tiny point. What engine could drive such brilliance? Nothing known could do that. Nothing except the gravity of a supermassive black hole devouring matter at the heart of a young galaxy. Around the same era, astronomers found an X-ray beacon in the constellation of the Swan, a bright, flickering glow that seemed to emanate from empty space. Careful measurements showed a visible star circling an invisible companion, tugged around by an object with immense mass packed into zero visible volume. It was as if an unseen phantom were whipping a star around like a weight on a string. This was the first strong evidence that black holes were not just theoretical. They were out there, lurking in our cosmic neighborhood. As evidence mounted, the scientific community underwent a profound shift. In the later decades of the 20th century, these objects went from speculative to central in astrophysics. The term black hole itself, coined around that time, captured the public imagination and the scientific reality, an inky hole in space that not even light can escape. By the late 20th century, what was once laughed off as a mere mathematical oddity had become an accepted part of the cosmic menagerie. Observations of stars at the centers of galaxies, whipping around unseen masses, indicated that something colossal and dark anchored them. One by one, the pieces fell into place. Almost every large galaxy seemed to harbor a monstrous black hole in its core, and smaller stellar mass black holes dotted the Milky Way, like hidden tombstones of long-dead stars. By the turn of the millennium, black holes were no longer fringe ideas. They were frontiers of exploration. We had begun detecting the very tremors of space produced when two black holes collide, and even imaging the silhouette of a black hole against a glowing cosmic backdrop. In just a few human generations, the concept journeyed from whimsical conjecture to concrete observation. Our ancestors imagined the possibility. Our parents' generation debated their reality. And in our time, we have come face to face with the dark heart of a galaxy, proving once and for all that these cosmic abysses are real. Each step of this historical journey, from the first whisper of a dark star to the bending of light in a revolutionary theory of gravity, to the discovery of celestial X-ray wraiths and blazing quasars, has been a rung on a ladder of revelation. And as we climbed that ladder, we moved closer and closer to the edge of the black hole itself. Now, standing here at this precipice, we carry with us the legacy of those insights and the awe of knowing that not only do black holes exist, but they are an integral part of our cosmic story. Now that science had accepted these entities as real, another question remained. What exactly is a black hole? At first glance, it seems to defy understanding, a hole rather than an object. But we can break down this enigma into parts, as one might describe the body of some mythical beast. The outermost surface of a black hole is not a tangible surface at all, but an invisible boundary known as the event horizon. This is the famous point of no return. It is the edge beyond which freedom ceases to exist. If anything, a star, a spacecraft, or even a ray of light ventures closer than this boundary, it will never re-emerge. To escape from that point would require moving faster than light itself, a feat the universe forbids. So the event horizon is like a one-way membrane in space. Things can fall in, but nothing comes out. To an outside observer, it appears as a perfect black sphere, a shadow where no light comes from. In truth, it isn't a physical surface, but a region of space defining where the pull becomes inescapable. Imagine the event horizon as the mouth of a great cosmic whirlpool. Just as water in a whirlpool spirals inward and cannot reverse course once it's too close to the drain, anything near a black hole spirals past this horizon and is swallowed. The closer you get, the stronger the pull. At a certain distance, that pull becomes absolute. This distance scales with the black hole's mass. A black hole 10 times the sun's mass has an event horizon only a few tens of kilometers across, whereas a black hole, millions of times the sun's mass, has a horizon that spans millions of kilometers. For perspective, a monster black hole can have an event horizon larger than our entire solar system. And yet, all that volume leads to something astonishingly small at the center. Deep inside, at the very core of a black hole, lies the singularity. This is the ultimate abyss, the heart of darkness, where density becomes infinite by our current understanding. Picture all the mass of a star, or even millions of stars, crushed into a point with no size. It's a place where our familiar ideas of space and time break down completely. In a non-spinning black hole, this singularity would be an infinitesimal dot. In a spinning black hole, it might be stretched into a tiny ring. Either way, it is hidden behind the curtain of the event horizon, forever out of direct sight. The singularity is like the secret at the black hole's center, a secret we cannot peek at because nature has drawn a veil over it. All we know is that it's where gravity has reached its crescendo, an infinity in a finite space. Between the event horizon and the singularity lies the black hole's interior, a one-way tunnel of sorts. Contrary to what one might expect, if you were falling in, you wouldn't actually see anything special as you pass the event horizon, at least not for a very large black hole. There is no sudden change in scenery, no shimmering wall. Locally, the laws of physics feel normal at the horizon. It's only once well inside that the space-time curvature becomes lethal. To any distant observer watching you fall, however, something very different happens. They would see you slow down and fade, never quite crossing the horizon, your image red-shifted to black. The event horizon is as much a divide in time as in space. From the outside, it seems to freeze moments on its edge for eternity. The black hole's event horizon can be thought of as a spherical prison. It holds within it everything that has ever fallen past, all the mass and information trapped like flies in amber on its boundary. Incredibly, a black hole can be completely described, as far as the outside world is concerned, by just a few numbers. Its mass, its spin, rotation, and perhaps an electric charge, though astrophysical black holes are expected to be essentially uncharged. Aside from those, a black hole carries no visible imprint of what fell into it. It does not remember whether it devoured a star, a planet, or a cloud of gas. All those details are lost behind the horizon. The beast has no hair, as physicists say, no distinguishing marks beyond its basic parameters. This simplicity is both elegant and eerie. It's as if the black hole digests everything into the same featureless state. The event horizon's size grows with each meal, like a belly expanding, but no other trace remains. Inside the horizon, space and time themselves trade roles. The pull inward isn't just a force, it becomes your future. Just as every next second of your life must carry you forward in time, every step you take inside a black hole must carry you further inward. There is no stopping, no standing still. The singularity lies in your future as inevitably as tomorrow. This is perhaps the strangest aspect of black hole anatomy. Once inside, falling to the center is as inescapable as time flowing forward. The geometry of space-time warps so extremely that every direction you could possibly move ultimately points you toward that central collapse. In sum, the anatomy of a black hole consists of an outer boundary where the world stops making sense to the rest of the universe, and an interior where the world stops making sense, period. A horizon where you vanish from the view of others, and a singularity where known laws of nature vanish from view. Between them, a warping labyrinth of space and time. It's a cosmic trapdoor. Below it, we cannot see. Beyond it, we cannot return. Yet this trapdoor is a fundamental part of our universe. From outside, it creates some of the most wondrous and terrifying phenomena we can observe. To truly know a black hole, we must understand both its unforgiving simplicity and its capacity to challenge reality at the deepest level. Every black hole has an origin story. For the most common black holes, those only a few times more massive than our Sun, the story begins with the death of a star. Picture a star perhaps 20 or 30 times the mass of the Sun, burning brightly for millions of years. Deep in its core, nuclear fusion fights a battle against gravity, generating light and heat that push outward and hold the star up. But eventually, even the mightiest star runs out of fuel. The furnace at the center flickers out, and outward pressure fades. In that instant, gravity, which had been patiently waiting, seizes the advantage. The star's core collapses inward in a fraction of a second. Matter rushes toward the center at incredible speeds. The collapse is so violent and sudden that it triggers a colossal explosion, a supernova. The outer layers of the star are blasted into space, shining as bright as 1 billion suns for a brief moment. But at the heart of this cataclysm, something even more remarkable happens. The core continues to collapse, tighter and tighter, until it forms a black hole. This newborn black hole might be only tens of kilometers across, even though it contains a mass equivalent to several suns. Imagine an object with the mass of our sun squeezed into a sphere the size of a city. The gravity of this remnant is intense. It's as if the death of the star punches a hole in the fabric of the universe. What remains is an ultra-dense corpse, a stellar mass black hole, left behind in the aftermath of the supernova's fury. In some cases, if the star was extremely massive or conditions are just right, the collapse may occur so fast that much of the star falls directly into the black hole without a supernova bang. A quiet death, forming a black hole in silence and darkness. These stellar mass black holes are scattered throughout galaxies like ours. In the Milky Way alone, astronomers estimate there could be tens of millions of them, hidden in the darkness. Most wander unseen, cold and quiet, because contrary to popular imagination, a black hole that is not actively feeding is essentially invisible. It doesn't glow or suck things in like a vacuum cleaner from afar. A lone black hole in empty space would be one of the most unassuming objects, undetectable to our telescopes, save for its gravitational pull. It's only when they interact with other objects that we notice their presence. Often, a stellar black hole reveals itself when it has a companion, say, another star orbiting it. If the two are close enough, the black hole's gravity can siphon gas from its stellar partner, drawing a stream of matter into its grasp. This gas spirals in, forming a swirling accretion disk around the black hole and heating up to extreme temperatures. In X-ray light, such a system blazes brilliantly. From Earth, we see these X-ray binaries as flickering beacons. It was in this manner that the first stellar black holes were confirmed, a visible star orbiting an unseen massive companion, its gas being inexorably pulled away and eaten. As that gas falls in, it lights up, crying out the presence of the invisible devourer. Within that disk, and near the black hole's edge, extraordinary processes occur. The intense gravity pulls one side of an infalling object harder than the other, a tidal force that can stretch objects into long strands. If an unlucky star or planet ventures too close to a stellar mass black hole, it could be pulled into a thin stream, a process poetically called spaghettification. The difference in gravity between the side of the object nearer the black hole and the side farther away is so great that it rips the object apart, stretching it as it goes. Fortunately, such extreme encounters are rare on human timescales, but they remind us how deadly these small black holes can be in close quarters. Stellar black holes may be small compared to their supermassive cousins, but they are by no means trivial. They pack tremendous gravity in a tiny package and can have profound effects on their surroundings. When two of them are born in a binary pair of stars, their deaths can lead to a spectacular reunion. The two black holes themselves can eventually spiral toward each other and merge in a violent embrace, shaking the fabric of the universe with gravitational waves. Such mergers momentarily produce more power than all the stars in the observable universe combined, though in gravitational energy rather than light. We'll hear more about those cosmic ripples later, but it is these stellar mass black holes dancing and colliding that have given us an entirely new way to observe the universe. In the grand tapestry of the cosmos, stellar mass black holes are like the ashes left after a great fire, the remnants of once brilliant stars. They mark the endpoints of stellar evolution and seed the galaxy with extremes of gravity. Each is a silent testament to a star that lived, shone, and died in a dramatic finale. They also serve as the starting point for a black hole's life. Given the right circumstances, a stellar black hole can gather more mass and grow, potentially merging with others to become something larger. But even on their own, these dark stellar remnants are fascinating and fearsome. They are, after all, direct connections to one of the most violent events in nature, a star's final collapse, and they embody the concept of death, giving rise to something new and strange. If stellar mass black holes are the ashes of individual stars, supermassive black holes are the colossal giants that reign over galaxies. These behemoths, found in the hearts of most galaxies including our own, contain millions to billions of times the mass of the Sun. Imagine something as heavy as an entire cluster of stars, all condensed into a region smaller than our solar system. These black holes are on a different scale altogether. They are cosmic anchors, so massive that their gravity binds whole galaxies. Stars in a galaxy's core swirl around an unseen center at astonishing speeds, compelled by the gravitational grip of a supermassive black hole lurking there. Our own Milky Way harbors such a monster at its nucleus. It's relatively modest as supermassive black holes go, about 4 million suns worth of mass. We cannot see it directly with our eyes, but we see the dance of stars around an apparently empty spot. Those stars whip around at velocities of thousands of kilometers per second, tracing orbits that betray an incredibly dense mass within. It's like watching leaves swirled by an invisible whirlpool. From their motion, we infer the whirlpool's presence. Occasionally, that dark center awakens. Bursts of high-energy flares have been observed when small clouds of gas or errant stars wander too near and get torn apart, feeding the beast and causing it to flicker in X-rays and infrared light. In other galaxies, the supermassive black holes are even larger and more voracious. The most massive black hole known weighs tens of billions of solar masses and would dwarf our entire solar system many times over. When such giants actively devour matter, they become the brightest objects in the universe. Paradoxical as it sounds, nothing is brighter than a feeding black hole. As gas and dust spiral into a supermassive black hole's maw, they heat up and blaze with light visible across billions of light years. This is the engine behind quasars and active galactic nuclei, those brilliant beacons at the cores of distant galaxies. In the early epochs of the universe, quasars shone like cosmic lighthouses, powered by supermassive black holes consuming matter at ferocious rates. They can outshine their entire host galaxies, a tiny central point releasing more light than the billions of stars around them combined. How does a black hole grow so big? It's a bit of a cosmic mystery, one that scientists are still piecing together. Some supermassive black holes likely began as smaller, stellar mass black holes that merged and swallowed gas over billions of years, gradually ballooning in mass. Galaxies often collide and merge with each other, and when they do, their central black holes can also coalesce, combining their mass. Over cosmic time, through galactic marriages and steady feeding, a black hole can climb the mass ladder into the supermassive range. However, we have observed quasars less than 1 billion years after the Big Bang that already house black holes of billions of solar masses. That is a very short time, cosmically speaking, for something to grow so large. It suggests that some black holes had a head start. Perhaps they were born big, formed by the direct collapse of enormous primordial gas clouds, or as the remnants of the very first generation of supermassive stars that lived fast and died young. It's possible that in the early universe, conditions allowed the creation of seed black holes much larger than any single star, giving them a running start. Once a supermassive black hole exists, it becomes a central player in its galaxy's evolution. It doesn't just sit quietly. Even when not actively gobbling matter as a quasar, Its presence can influence star formation and the dynamics of the galaxy. It acts as a sort of cosmic governor. When it feeds, it can erupt in jets and winds, which we'll explore soon, pumping energy back into the galaxy. These outflows can heat up or blow away the gas that would otherwise form new stars, thereby regulating the galaxy's growth. In this way, the black hole at the center and the galaxy around it seem to grow in tandem, each influencing the other. Astronomers have discovered an intriguing relationship. The mass of a galaxy's central black hole is roughly proportional to the mass of the galaxy's central bulge of stars. They scale together, as if the black hole and the galaxy have been co-authoring a story over eons, keeping each other in check. Supermassive black holes are, in many ways, cosmic paradoxes. They are enormously destructive. Any star that ventures too close can be ripped apart. Any gas cloud will be consumed. Yet, in their destruction, they create. The energy they release can trigger shocks in distant gas clouds, sometimes compressing them enough to spark the birth of new stars at a galaxy's outskirts. They shape the structure and fate of galaxies. In their quiet phases, they are dark and undetectable. In their active phases, they are the brightest beacons in existence. They sit at the centers of galaxies for billions of years, like silent puppet masters orchestrating cosmic dramas. Each one is a reminder that in the universe, sometimes the most powerful furnace of energy is not a shining star, but a dark pit that paradoxically radiates brilliance when the time comes to feed. Not all black holes fit neatly into the categories of stellar or supermassive. Astronomers have long suspected the existence of black holes that are in between, the so-called intermediate mass black holes. These would weigh perhaps a few hundred to a few 100,000 suns, bridging the gap between the star-sized corpses and the galactic giants. For decades, they remained elusive, like phantom missing links in the cosmic record. If they exist, they might hide in the centers of globular clusters, spherical swarms of stars, or as the remnants of mini-galaxies that merged into bigger ones. There have been tantalizing hints. A powerful X-ray flare in a distant galaxy that suggested an object of about 50,000 solar masses tearing apart a star. Stars in certain dense clusters moving in ways that hinted at an unseen massive presence at the core. One by one, these clues have emerged, but definitive proof has been hard to pin down. Intermediate black holes are shy, revealing themselves only subtly. The universe, however, gave us a nudge in recent years. When observatories on Earth began to listen to the universe using gravitational waves, ripples in space-time, we detected the collisions of stellar mass black holes by the dozen. In one such cataclysmic event, two hefty black holes merged and formed a new black hole heavier than any single star's collapse could produce, an object of about 150 solar masses. For a moment, we had direct evidence of an intermediate mass black hole born from the union of smaller ones. It was a brief glimpse. The merger itself was over in seconds and the waves faded, but it confirmed that nature can make black holes in this mass range. The question remains, do intermediate black holes persist independently in the universe, slowly grown over time, or are they mostly stepping stones, formed in rare mergers and destined either to keep growing or to stay hidden in remote corners? Scientists continue to hunt for these middling monsters, each candidate citing perhaps a peculiar source of radiation or a gravitational lensing effect on background starlight, brings hope that we will finally catch one in the act of simply being itself, neither small nor supermassive, but something intriguingly in between. Now pivot from the present back to the very beginning of time. There is another hypothetical class of black holes, even more mysterious and elusive: primordial black holes. These would not come from stars at all, but from the high-energy, high-density chaos of the early universe itself. In the first second after the Big Bang, the universe was an extremely hot soup of energy and particles. Tiny fluctuations in density, quantum wrinkles in the fabric of the young cosmos, could have been magnified during cosmic inflation, the rapid expansion at the universe's dawn. In some regions, the concentration of matter might have crossed a critical threshold, collapsing into black holes mere moments after time began. These primordial black holes could, in theory, have had masses ranging from tiny fractions of a gram to thousands of suns, depending on the size of the fluctuation that birthed them. Imagine black holes as small as mountains or even asteroids zipping through the cosmos. Some might have been so low in mass that over billions of years they would entirely evaporate via Hawking radiation, a process we'll discuss later. Heavier ones could survive to the present day, scattered throughout space as fossil relics of the Big Bang. Primordial black holes offer a tempting explanation for some of our universe's puzzles. Could they be a component of the dark matter that makes up much of the universe's mass? If so, swarms of unseen primordial black holes might be drifting through galaxies, each too faint to notice individually, but collectively exerting gravitational influence. Researchers have looked for signs of them, flashes of light from a tiny black hole evaporating at the end of its life, or subtle gravitational lensing events when one passes in front of distant stars. So far, these searches have come up empty or inconclusive, placing limits on how many primordial black holes could exist and in what mass ranges. If very small ones had formed, most would be gone by now, having evaporated in a final burst of gamma rays. If medium-sized ones had formed, they cannot be too numerous, or we would have seen their effects on starlight statistically. The possibility remains that primordial black holes might exist in a narrow range of masses, quietly contributing to the dark matter. It's a fascinating idea that alongside particles and atoms, some portion of the unseen mass of the universe could actually be an ancient population of black holes. Both intermediate mass and primordial black holes highlight how much we still have to learn. Intermediate black holes challenge us to find objects that are neither the result of a single star's death nor the long-cultivated giants in galactic centers, but something formed by unique circumstances. Perhaps the merger of many stars or black holes in a dense cluster, or the direct collapse of a massive early star that wasn't quite a galaxy's nucleus. Primordial black holes, on the other hand, challenge our understanding of the early universe. They ask whether nature forged black holes before stars even existed. If they did, then black holes might predate galaxies themselves, sprinkling the cosmos with gravitational traps from time immemorial. These lesser-seen members of the black hole family, if they exist in abundance, could fill important chapters in the story of our universe. Intermediate black holes might explain how the supermassive ones got such a jumpstart, perhaps serving as the seeds that grew into quasars. Primordial black holes could rewrite our theories of cosmology and dark matter. As of now, they remain subjects of intrigue and investigation. They remind us that not all black holes announce themselves readily. Some lurk in mass ranges or epochs that we have only begun to explore. The cosmic story of black holes is far from complete. There are still shadowy characters that may yet emerge from obscurity. So far, we've considered black holes themselves, what they are, where they come from. But black holes do not live in isolation. Their presence dramatically affects their surroundings. When they feed, they often become the centers of the most radiant displays in the universe. The key lies in the accretion disk, the maelstrom of matter that gathers around a black hole as it pulls in gas, dust, or the occasional star. As material falls toward a black hole, it is forced into a spiraling orbit, like water circling a drain. This creates a flattened disk of orbiting debris around the black hole. The closer the matter gets to the black hole, the faster it races, whipping around at a significant fraction of light speed. Friction and turbulence in the disk heat it to extraordinary temperatures. What was once cold interstellar gas or a star's outer layers becomes a ferocious plasma tens of millions of degrees hot. At such temperatures, it glows fiercely, typically in high-energy light like X-rays and ultraviolet. Paradoxically, a feeding black hole is often surrounded by a blaze of light, We don't see the black hole itself, but we see this brilliant last gasp of material as it struggles to hang on before crossing the horizon. Imagine looking at a black hole being fed by a stream of gas from a nearby star. You would see a glowing disk encircling a dark center. The inner edge of the disk orbits so fast and is so distorted by gravity that its light is bizarrely stretched and bent. On one side of the disk, where the orbiting material comes toward us, the light is boosted, blue-shifted, and bright. On the opposite side, where it moves away, the light is weakened, red-shifted, and dimmer. This asymmetry can actually be observed, a gravitational fingerprint on the disk's light. Above and below the disk, the black hole's gravity warps photons into a halo or ring, the photon ring, a circular image of light that skims just outside the event horizon and swings around. Together, the disk and these warped pathways of light create an image of a glowing donut-like structure, a beacon signaling a black hole's presence. But the drama doesn't end with the disk. In many cases, especially with supermassive black holes, twin jets are launched, colossal, narrow beams of particles and energy that shoot out from the poles of the black hole's spinning disk. These jets are like cosmic blowtorches drilling through space. They can extend for thousands, even millions of light years, far beyond their host galaxy's bounds. To put that in perspective, a jet from a galaxy's center can be so large that, if we could see radio waves with our eyes, it would span the sky, even though it originates in a nucleus millions of light years away. These jets contain matter accelerated to near light speed, hence relativistic jets. They are composed of charged particles, electrons and heavier nuclei, or perhaps electron-positron plasmas, and are threaded by intense magnetic fields. The prevailing theory is that the rotation of the black hole and the disk's magnetic fields can fling some of the infalling matter back out, turning it into twin jets that blaze out along the axis of rotation. The physics at the base of these jets is complex, but we can appreciate the outcome. A black hole can both devour matter and spit some of it back out in dramatically transformed fashion. The jets shine in radio waves, X-rays, and gamma rays. In fact, some of the brightest radio sources in the sky are the lobes of energized gas at the ends of these jets, where they ram into intergalactic material and deposit their energy. It's a bit like a fire hose blasting into a pool of water. Where the stream hits, great billows form, radio lobes, that mark where the jet dumps its power. Accretion disks and jets are not just showpieces. They play a crucial role in the cosmic ecosystem. The disk is the black hole's dining table, and how fast a black hole grows is determined by how much matter the disk funnels in. Disks can flicker and flare when chunks of matter fall in, giving astronomers a way to track the feeding habits of black holes. Jets, on the other hand, carry away tremendous energy and momentum. They can heat up the surrounding gas for hundreds of thousands of light years, even stopping new stars from forming by blowing out or heating the raw material. Alternatively, the shock of a jet blasting into gas clouds can compress them and induce new starbirth at the edges. In either case, jets mean that a black hole's influence isn't confined to its immediate neighborhood. It can reach far beyond, affecting the fate of its galaxy and even the environment of intergalactic space. From a storytelling perspective, it's as if the black hole has two faces: the gluttonous eater, the accretion disk, that glows from the feast, and the mighty dragon, the jets, that breathes fire back into the cosmos. Amazingly, we have actually photographed something akin to that eater's face. The first image of a black hole's immediate vicinity showed a bright ring, the glow of the disk and the photon ring, outlining the silhouette of the black hole itself. It was light from an accretion disk, 55 million light years away, that provided the ink to sketch the portrait of that black hole's shadow. As for jets, we have imaged those too. For instance, the supermassive black hole in that very galaxy we photographed has a jet visible as a bright streak shooting out from the galaxy's core in radio light. A accretion disks and jets turn black holes from silent gobblers into cosmic performers. They ensure that even as a black hole cloaks itself in darkness, the act of feeding breaks that silence with radiant energy and astonishing dynamism. It's a spectacle of creation and destruction entwined, matter falling in to be destroyed, energy flung out to perhaps create anew elsewhere. In the grandeur of a galaxy, the brightest core and the longest jets both proclaim the presence of a once invisible singularity, making itself known by the havoc and brilliance it unleashes. Black holes may be small compared to their host galaxies, but they wield influence far beyond their size. In the cosmic ecosystem, a supermassive black hole at a galaxy's core can function like a regulator, sometimes a nurturer, other times an executioner of star formation. It is astonishing to realize that an object which occupies a tiny fraction of the galaxy's volume can govern the fate of billions of stars spread across tens of thousands of light years. Yet through energy and gravity, it does. When a supermassive black hole feeds ravenously, it enters what we call an active phase. The accretion disk and jets we discussed pump out stupendous amounts of energy into the galaxy's innards. This outpouring acts like a cosmic wind or heater. Gas that would have cooled and condensed into new stars can instead be blown outward or warmed so much that it cannot clump to form stars. Think of a gardener burning dry leaves. The smoke drives away insects and seeds alike. Similarly, the feedback from a quasar, an active black hole, can clear out a galaxy's stellar nurseries. Whole reservoirs of gas get ejected into intergalactic space, or stirred so violently that they remain too hot to collapse into stars. The result? The galaxy's prolific starbirth is quenched. It ages. Its existing stars grow old and red, with few new ones to take their place. Many giant elliptical galaxies, immense balls of old red stars, likely had such a phase in their youth. Their central black holes ignited and effectively said, "No more stars shall form here," rendering them red and dead galaxies by cosmic middle age. On the flip side, black hole influence isn't purely destructive. The energy blast from a central black hole can also compress gas in certain regions, triggering bursts of star formation just outside the affected zone. It's as if the same gardener prunes in one place but scatters fertilizer in another. Observations show instances of new stars blooming at the edges of cavities carved out by black hole-driven winds in galaxies and galaxy clusters. The interplay is complex. Depending on the galaxy's size, the black hole's power, and the distribution of gas, the outcome can be a balance between suppressed starbirth in some areas and stimulated starbirth in others. Even in its quiet state, a supermassive black hole's gravity can subtly steer the evolution of its galaxy. It maintains a gravitational grip on stars in the dense galactic core, helping to keep them in more ordered orbits. Without a heavy anchor at the center, some galaxies might have looser, more chaotic stellar swarms in their nuclei. In our Milky Way, for example, the central black hole, while calm now, binds a cluster of stars that orbit it like planets around an invisible sun. If that black hole weren't there, those central stars might scatter or be flung away. Instead, they circle obediently, and their orbits have allowed us to measure the black hole's mass precisely by watching their celestial choreography. The relationship between a galaxy and its central black hole appears almost symbiotic. Over billions of years, as galaxies grew through mergers and gas accretion, their black holes grew in tandem. When the black hole became too active, it would curtail the galaxy's growth by cutting off star formation. This self-regulating dance likely explains a key observation. The mass of a supermassive black hole correlates with the velocity of stars in its host galaxy's bulge and the bulge's mass. It's as though every galaxy's evolution carries the imprint of a long conversation between it and its black hole. Sometimes a friendly chat, sometimes an argument, but one that ultimately reaches an equilibrium. Consider a massive cluster of galaxies, thousands of galaxies, held together by gravity. At the heart of the cluster usually lies a gigantic elliptical galaxy, itself harboring a supermassive black hole. We see giant bubbles in the hot gas that fills these clusters, blown by repeated jet outbursts from the central black hole. Those bubbles rise like hot air balloons, distributing energy throughout the cluster's core and preventing gas from cooling too quickly. In doing so, the black hole indirectly controls star formation on the scale of an entire cluster, not just a single galaxy. The effect is so pronounced that without black hole feedback, simulations of the universe predict far more stars forming in big galaxies than we observe. The black holes act as brakes on runaway star birth. On more human timescales, a galaxy's central black hole can also be an agent of dramatic events. It can capture and shred a wayward star, causing sudden flares that outshine the entire galaxy for a time. It can influence the orbits of other black holes or dense objects, potentially sending them spiraling into the center. Over millions of years, these processes shape the nuclear star cluster and the inventory of exotic objects, like neutron stars and smaller black holes, near the core. In essence, a black hole's influence on its galaxy is like that of a heart on a body. When it beats strongly, in the active quasar phase, it sends powerful pulses that can be life-sustaining in moderation or harmful in excess. When it rests, the body is calm, but still subtly under the heart's control. Galaxies and their black holes are intertwined across cosmic time. One grows, the other responds, in a complex feedback loop. So when we gaze at a serene galaxy, glittering with billions of stars, we should remember that at its center likely resides a black hole that has, in earlier times, blown fiery winds and set the stage for how those stars came to be arranged. Black holes, though tiny relative to their expansive realms, act as cosmic conductors, ensuring galaxies do not grow without limit, and that the story of star formation has both pauses and crescendos. Despite all these powerful clues and influences, for generations, black holes remained unseen directly, only inferred. They lived in equations, in the motions of stars, in bursts of radiation, but not in any image. That changed in a defining moment for science and human curiosity. Not long ago, we managed to capture an image of the unseeable. A global alliance of radio telescopes, spread from mountaintops to deserts across the Earth, worked in unison, effectively turning our entire planet into one giant eye, sharp enough to gaze across galaxies. They set their sights on a supermassive black hole in a nearby cluster of galaxies, aiming to observe the silhouette cast by its event horizon. This target was a leviathan billions of times the mass of the Sun, surrounded by a bright disk of infalling gas, an ideal candidate to reveal a black hole's visage. After years of meticulous planning, synchronization, and data analysis, the effort bore fruit. The world was presented with a haunting picture, a fuzzy, glowing ring of gold and orange, with a deep, dark center. It was immediately recognizable as something extraordinary, the shadow of a black hole, seen for the first time. That dark center was the imprint of the event horizon, a hole in the light where photons were missing because they had been pulled into the abyss. The ring around it was light from the accretion disk, bent and magnified by gravity into a halo. We were gazing, effectively, at the silhouette of a phenomenon that had only existed in theory until then. The image was both humbling and exhilarating. In its blur and simplicity, it confirmed decades of theoretical work. The size and shape of the black hole's shadow matched what general relativity predicted for an object of that mass at that distance. It was a direct affirmation that our understanding of gravity holds true even in nature's most extreme crucible. People around the world reacted with awe. Some described the image as witnessing the gates of hell or the eye of Sauron, grasping for metaphors to fathom the intense reality of what we saw. But beyond the drama, This was a triumph of human cooperation and ingenuity. To photograph a black hole's shadow, one must capture details as fine as seeing an orange on the moon from Earth. That required linking telescopes across continents, timing their observations to within billionths of a second, and hauling petabytes of data to be combined. It was an achievement at the very edge of what technology and teamwork could accomplish. The significance of this first image extends beyond one black hole. It opened a new window into studying these objects. We can now, in principle, see how reality behaves just outside the event horizon. By analyzing the brightness and shape of that ring, scientists can test how well our theories hold up and search for tiny deviations that might hint at new physics. The image also drives home a more philosophical point. Black holes are no longer mere abstractions. We have seen one. It is real in the most direct sense. The concept leapt from chalkboards and computer simulations into a picture we can frame and behold. In that sense, a black hole became tangible. Buoyed by this success, astronomers didn't stop at one. They turned the Earth-sized telescope network toward the quiet giant at the center of our own Milky Way. This was a tougher challenge. Our black hole is smaller, and the ring of light around it changes on timescales of minutes, as opposed to the relatively stable, hours-long patterns in the first target. After heroic efforts to freeze the flicker with algorithms and to tease out the signal from turbulent interstellar gas, they produced another image, a similar glowing ring, but this time surrounding our galaxy's very own dark heart. We now have portraits of two black holes, one a monstrous engine in a distant galaxy, one the somewhat gentler heavyweight in our backyard. They are family photos of sorts, revealing that no matter the scale, a hungry black hole paints the same telltale picture. Seeing that shadow for the first time was like finally meeting a legendary creature face to face. It was the dragon's outline emerging from the cave. And true to the best stories, it was neither a disappointment nor a monstrosity beyond comprehension. It was a bit of both in its strange beauty. The bright ring told of incredible energies and the dance of photons in curved space-time. The dark shadow spoke of the absolute darkness within, where no information escapes. With that image, humanity stepped closer to the black hole's edge than ever before, not in person, but in perception. It's a moment that will be remembered as a milestone, the day we captured a piece of a black hole's essence on camera. In the future, these images will only get sharper. We may witness movies of gas swirling, see jets at their genesis, watch as black holes feed and change in real time. But nothing will quite compare to that first glimpse, the moment the darkness of a black hole was illuminated by the light it itself sculpted. It affirmed that by persistent curiosity and ingenuity, we can reveal the universe's deepest secrets. The black hole's shadow is no longer just a calculation, it has become a sight to behold. For all the images and light black holes can produce indirectly, one of the most groundbreaking discoveries in recent times came not from seeing a black hole, but from hearing one, or rather feeling one through the fabric of space-time. In the quietness of a high-tech observatory, long tunnels with laser beams reflected back and forth suddenly sensed an almost imperceptible tremor. In that faint jitter of light was encoded an event of unfathomable violence. Two black holes, far across the universe, had collided and merged into one. When black holes spiral toward each other, they create ripples in space-time itself. Like a stone dropped in a pond sends out waves on the water's surface. These ripples are gravitational waves. As two black holes draw close, their dance quickens. They circle each other faster and faster, nearing the speed of light, and the gravitational waves they emit increase in frequency and strength. In the final moments, the two black holes crash together, merging into a single, larger black hole. This merger rings space-time like a gigantic bell, sending out a storm of gravitational waves in all directions. Then, as the disturbed new black hole settles into its final shape, the waves taper off. If one could listen to these waves by converting their frequencies into sound, it would resemble a brief chirp, a rising tone that suddenly cuts off. That chirp is the death song of two black holes becoming one. For over a century, after general relativity predicted gravitational waves, they remained elusive. They stretch and squeeze space itself, but by the time they reach us from distant events, the effect is minuscule, far smaller than an atom. Detecting them required extreme ingenuity. Finally, humans built instruments capable of measuring distance changes as small as a fraction of a proton's width. And then, one day, the signal came. The instruments recorded the characteristic chirp. We had, for the first time, directly detected gravitational waves, and they came from a binary black hole merger. The news reverberated around the world. We had heard black holes colliding. This achievement opened a new era of astronomy. No longer were we confined to using light, electromagnetic waves, to observe the cosmos. We could now use gravitational waves as well. Black holes, which are often invisible to traditional telescopes, became audible through these cosmic vibrations. In the years since that first detection, dozens of black hole mergers have been recorded. Each detection is essentially the ghostly record of a cataclysm in the distant universe, often billions of years ago, before multicellular life existed on Earth, whose faint echo is only now washing over us. Through gravitational waves, we've discovered black holes of sizes we hadn't observed before. Some were much more massive than any stellar black hole known from X-ray observations. This told us black holes can grow by merging with each other, and perhaps that some formed from stars in environments we hadn't fully envisioned. We've detected black holes spinning, and even cases where two merging black holes had spins tilted at odd angles to their orbits, causing them to wobble like tops as they merged. Subtle effects encoded in the gravitational waveform. The beauty of gravitational wave astronomy is that it gives us a way to sense the universe that is completely different from sight. It's like gaining a new sense organ. Black holes are at the forefront of this new sense because they often merge invisibly. No light escapes them, and if they have little gas around, the merger emits no light. Without gravitational wave detectors, two black holes could collide entirely unnoticed by all our telescopes. Now we can catch them in the act routinely. Each time two black holes merge, a bit of their mass is lost, up to a few percent of the total, converted directly into gravitational wave energy. For a brief moment, the power of that event exceeds the light from all stars in the observable universe combined. Yet by the time those ripples reach us, they are so faint that it takes the most sensitive instruments ever built to detect them. The first detection was a triumph not just of technology, but of human imagination. We had imagined these black hole dances and their cosmic music, and then built the means to hear it. There's a profound emotion in knowing that the gentle rising chirp in a detector's speaker is in fact the ripple of two black holes, each perhaps 30 times the mass of the Sun, colliding a billion light years away. It connects us to an event so remote and extreme, yet through physics and engineering, it becomes almost intimate, a tiny motion in mirrors here on Earth, carrying the story of that distant tragedy. Gravitational waves have enriched our understanding of black holes. They confirmed that black holes do merge as predicted, and that such mergers are common enough to be detectable. They allowed us to test general relativity in the strongest gravitational fields. So far, the predictions hold perfectly. The waves match the theory's expectations to remarkable precision, and these waves may eventually reveal new surprises. Perhaps signals from black hole neutron star collisions. Indeed, we've caught those too. Or one day, the slow in-spiral of supermassive black holes, whose long waves we might detect with pulsar timing arrays or space-based detectors. Each new type of wave is a new chapter of cosmic storytelling. For black holes, gravitational waves are like a voice, a bass vibration echoing through the cosmos. We have begun to eavesdrop on their conversations. With each detection, we expand our sensory picture of the universe, feeling more deeply the dynamic, restless activity that light alone could not reveal. It's an unfolding story of the cosmos where black holes often take center stage, not in the spotlight of brightness, but in the subtle tremors that announce the most dramatic collisions known. Black holes, for all their power and finality, harbor a subtle secret. Given enough time, they are not completely black, nor do they last forever. About half a century ago, a bold theoretical physicist blended quantum theory with the theory of black holes and arrived at a startling conclusion. The very emptiness around a black hole's event horizon isn't truly empty. According to quantum physics, even vacuum teams with fleeting particle-antiparticle pairs that pop into existence and then annihilate and disappear almost immediately. One could ask, what happens to these pairs right at the edge of a black hole? The answer that emerged was astonishing. If a pair of virtual particles forms near the event horizon, it's possible for one particle to fall into the black hole while the other escapes before they can annihilate each other. To an outside observer, that escaping particle looks as if it has been emitted by the black hole. But nothing, conventionally, escapes a black hole. So how can this be? The trick is that the black hole loses a bit of its mass energy to make it happen. The particle that falls in effectively carries negative energy from the outside perspective, subtracting from the black hole's mass, while the one that escapes carries positive energy away as radiation. The net effect is that the black hole radiates particles and light as if it were a hot object, a black body with a certain temperature. This phenomenon, now known as Hawking radiation, gives black holes a temperature inversely proportional to their mass. Small black holes are hotter and evaporate quickly. Large black holes are exceedingly cold and evaporate extremely slowly. For a stellar mass black hole, the temperature is tiny, far colder than the microwave background glow of the universe, essentially undetectable with current technology. Such a black hole would take many times the current age of the universe to evaporate significantly, making it effectively immortal on any practical timescale. But for a tiny black hole, say one with the mass of a mountain, the temperature would be higher, though still very low by everyday standards. As the black hole radiates, it loses mass, and as it loses mass, it gets hotter and radiates faster. This leads to a runaway crescendo at the end of a black hole's life. In its final moments, if it ever becomes very small, it would radiate furiously, heating up to billions of degrees and likely exploding in a burst of high-energy particles and gamma rays. No such final burst has ever been observed, which isn't surprising. If primordial black holes of small size were common, we might have seen one by now as a mysterious explosion in the sky. Their absence tells us that if primordial black holes exist at all, they're either large enough to still be around, or they were never abundant. Still, the insight that black holes evaporate was profound because it married quantum mechanics with gravity in a tangible way. It showed that black holes are not one-way traps in the absolute sense. They can very slowly leak energy, and presumably information, back out into the universe. They obey a version of the second law of thermodynamics. They have entropy, proportional to the area of their event horizon, and a temperature, and they will eventually come to thermal equilibrium with the rest of the universe by radiating away. The idea that black holes evaporate forces a change in perspective. These cosmic abysses are not eternal. Given enough eons, even the mightiest black hole will shrink and ultimately vanish in a final flash. In a universe far, far into the future, long after the stars have burned out and galaxies have dispersed, one can imagine the last black holes sizzling away into a faint glow, like embers in the darkness, until they wink out. It is a melancholy yet beautiful vision of an ultimate heat death. Even the darkness itself evaporates. For present-day astrophysical black holes, Hawking radiation has no noticeable effect. A black hole continuously feasting on surrounding gas or merging with others grows far faster than it could ever evaporate. In fact, The faint trickle of Hawking radiation is overwhelmed by the bath of cosmic microwave background radiation still filling the universe. Paradoxically, the universe's residual light feeds energy into a black hole faster than the hole loses it. Evaporation becomes important only for hypothetical, isolated small black holes. But the theoretical importance of Hawking's discovery is immense. It provides a crucial link between three pillars of physics: quantum theory, general relativity, and thermodynamics. In the gentle hiss of Hawking radiation, we see a hint of how these frameworks unify. The notion that the event horizon's area corresponds to entropy, and that black holes have a finite temperature was shocking at first, but it has become a cornerstone of modern theoretical physics. Hawking radiation also set the stage for one of the deepest puzzles in physics, the information paradox. If a black hole eventually evaporates completely, what happens to all the information about the things that fell into it? Is it encoded somehow in the Hawking radiation, or is it truly lost to the universe? This question challenges our understanding of how quantum mechanics works on cosmic scales. But regardless of that puzzle, which we will delve into next, Hawking's discovery transformed black holes from deadly, unchanging endpoints into dynamic objects with life cycles of their own. They can be born, they can grow, and yes, they can slowly die. It's poetic in a way. An entity that swallows everything can, in the end, give back to the void. A black hole evaporating is like a drop of ink spreading out into a vast ocean. The concentrated darkness dilutes into faint radiation, returning its energy to the wider universe. No one has witnessed this process directly, and perhaps no one ever will, given the immense timescales. But the equations speak, and they tell us that even black holes whisper ever so softly and fade away when left alone. Here, we confront perhaps the most confounding riddle posed by black holes. It arises from the clash of two deep principles: the absolute gravity of a black hole and the inviolable laws of quantum physics. We've learned that black holes can evaporate over time via Hawking radiation. That radiation, as originally calculated, appears to carry no information about what fell into the black hole. It's featureless, like heat from a furnace. But quantum mechanics has a stringent rule: information cannot be destroyed. If you know the exact quantum state of a system, it will evolve into another exact state. In principle, you can always reverse the process and recover the initial information. Burning a book, for example, scrambles the information into ash and smoke. But in theory, ignoring practical limitations, that information is still present in the arrangement of particles and could be reconstructed. A black hole, however, seems to take in a book and later evaporate without a trace of what was written in it. The information, by all accounts, would be gone. This is the black hole information paradox. When it was first suggested that a black hole's evaporation would destroy information, it shook the physics community. It wasn't just about black holes. It struck at the heart of what quantum physics means. If black holes can truly erase information in a way that nothing else we know of can, then our understanding of physics at a fundamental level is incomplete or wrong. Either quantum mechanics, which has never failed a laboratory test, would need revision, or our picture of black hole evaporation was missing key details. The paradox can be summed up in a stark scenario. Throw an encyclopedia into a black hole. From the outside, you can no longer read it. The information in those pages is effectively lost to the observable universe. Over a fantastically long time, suppose the black hole evaporates completely into featureless Hawking radiation, like a final puff of steam. Now, where is the information that was in that encyclopedia? Quantum theory insists it must still be in the outgoing radiation somehow, perhaps encoded in subtle correlations between particles. But Hawking's original calculation implied it was not. It was simply lost. This contradiction has led to decades of intense thought and debate. Many ideas have been proposed to resolve the paradox. Some suggested that perhaps black holes don't evaporate entirely. Maybe they leave behind some kind of stable remnant that stores the information, though that concept raises other issues. Others considered that when black holes evaporate, they might spawn a baby universe that carries away the missing information, sequestered from our own universe. A leading perspective today comes from the holographic principle, which posits that all the information that falls into a black hole is not lost, but is somehow stored on the event horizon's surface, like a cosmic ledger or hard drive with an enormous capacity measured in bits per area. In this view, as the black hole evaporates, the information slowly gets encoded in the Hawking radiation in highly scrambled form, so scrambled that Hawking's original calculation, which treated the radiation as perfectly random, missed the subtle way information could leak out. In recent years, theoretical breakthroughs using ideas from quantum information theory and holography have given tantalizing evidence that information does indeed escape in the Hawking radiation, albeit in an extremely encrypted form. It appears that the radiation is not perfectly featureless after all. Tiny deviations from a perfect thermal spectrum carry away the hidden message of what fell in. As the black hole shrinks, these correlations become significant and ensure that by the end of evaporation, no information is truly lost. However, exactly how this happens requires physics beyond what we currently fully grasp, essentially a true theory of quantum gravity. One provocative proposal was the idea of firewalls. Some researchers speculated that perhaps the interior of an old black hole, one that has evaporated down to a small size, might not be the smooth continuation of space that general relativity predicts. Instead, a searing wall of high-energy quanta at the horizon could incinerate anything trying to enter or exit, which might enforce information conservation at the expense of something called the equivalence principle, the idea that falling through a horizon should feel uneventful. This idea is controversial because it essentially says that the event horizon might become a violent place in certain conditions, contradicting the classical notion that crossing a big black hole's horizon is uneventful. The very fact that serious scientists would entertain such an outlandish concept shows how pressing the information paradox is. It seems some cherished principle of physics must give way, and they are debating which one. Amid these debates, a common sentiment has emerged. The information paradox is not just a puzzle about black holes, it's a beacon pointing toward a deeper understanding of nature. To fully resolve it, we likely need a successful theory of quantum gravity, a framework that unifies general relativity, our theory of the cosmos, with quantum mechanics, our theory of the microscopic. In chasing the paradox, physicists have developed new ideas, like holography and quantum entanglement arguments, that have already yielded partial insights. Most physicists now suspect that when we finally have a full theory of quantum gravity, be it an evolved form of string theory, loop quantum gravity, or something else, the paradox will dissolve, and we will see that no information was truly lost to begin with. From a philosophical standpoint, the information paradox forces us to consider what identity means in a physical sense. If a person falls into a black hole, is the information that constituted their being, every particle, every quantum state of their body, preserved in principle, or is it irretrievably destroyed? It's a mind-bending contemplation. Nature seems to guard information as a fundamental currency, yet a black hole seems to be a supreme destroyer of it. Resolving that contradiction may tell us whether the universe is ultimately deterministic and information-preserving, or whether there are places, like black holes, where the usual rules falter in a profound way. As of now, the consensus among theorists leans toward information being preserved. Black holes probably do not violate the laws of quantum mechanics at the fundamental level. Instead, they challenge us to better understand those laws under extreme conditions. The paradox has been a driving force behind some of the most creative theoretical work of the last half-century. Slowly, like a code being deciphered, pieces are falling into place. entropy corresponding to horizon area, radiation carrying information in subtle ways, horizons having microstates. All hint that black holes are puzzles meant to be solved, and in doing so, we learn the language of a deeper reality. The information paradox stands as both a warning and an inspiration. A warning that something in our knowledge is incomplete, and an inspiration that by completing it, we will grasp a more profound truth about how the universe works. Black holes are more than just astrophysical objects. They are theoretical laboratories for the frontier of physics. At the meeting point of extreme gravity, quantum effects, and thermodynamics, black holes present a crossroads where our current theories collide and intertwine. We've already seen hints of this, the notion that black holes have entropy and temperature, thermodynamics, that they evaporate via quantum processes, and that their existence is predicted by general relativity. In a sense, a black hole is where the cosmic, the very large, meets the quantum, the very small, and understanding them fully requires a theory that can handle both, a theory of quantum gravity. The laws of black hole mechanics, formulated in the early 1970s, bore an uncanny resemblance to the ordinary laws of thermodynamics. They stated, for example, that the area of a black hole's event horizon never decreases, analogous to entropy disorder, never decreasing in a closed system, and that there is a quantity, surface gravity, analogous to temperature. Initially, these parallels were thought to be just analogies. But Hawking's discovery that black holes radiate gave literal meaning to them. Black hole entropy is real and enormous. A black hole of a few solar masses has vastly more entropy than the sun, and black hole temperature is real, though tiny for large holes. This realization was a beacon illuminating a deeper truth. Gravity, quantum mechanics, and thermodynamics are intimately connected. It's as if three very different languages, the language of curved space-time, the language of particles and probabilities, and the language of heat and energy, all converge in describing a black hole. To speak fully about a black hole, one has to be multilingual in physics. This is both inspiring and daunting. It suggests that our current separation of physics into different domains, quantum versus cosmic, for instance, is artificial. There is a unity to be found. Many physicists believe that to resolve the information paradox and truly understand the singularity at a black hole's core, we need a workable quantum theory of gravity. Various approaches are being explored. String theory, for example, posits that fundamental entities are tiny vibrating strings, and that black holes might be composed of very tightly wound strings or brains. In some string theory calculations, scientists can account for the entropy of certain black holes by counting the quantum states of those strings, and the result exactly matches the Bekenstein-Hawking entropy, the formula relating entropy to horizon area. This was a triumph, indicating that a quantum gravity theory can, in principle, explain black hole thermodynamics. It's as if string theory peeked behind the event horizon and saw all the microscopic degrees of freedom that make up a black hole's enormous entropy. Another concept that has emerged is the holographic principle, which we've touched on. It suggests that everything that happens inside a volume of space, like the interior of a black hole or even our observable universe, could be described by information encoded on the boundary of that volume, like the event horizon surface. In a holographic description, the three-dimensional interior is projected from data on a two-dimensional surface, similar to how a hologram encodes a 3D image on a flat film. Remarkably, a prime example of this principle is a result from string theory called the ADS-CFT correspondence. In that scenario, a gravitational world in a certain kind of space with an extra dimension is exactly equivalent to a quantum field theory without gravity on its boundary. In such a duality, a black hole in the interior corresponds to a hot thermal state in the boundary theory. The information paradox in the gravitational picture becomes a much more tractable question in the boundary picture, where there is no paradox because standard quantum theory applies. This duality has provided strong evidence that black holes, when viewed with the right theoretical lens, do not truly destroy information. The information is encoded in subtle ways, consistent with quantum mechanics, just not in ways we find obvious from our usual perspective. Beyond string theory, other approaches like loop quantum gravity attempt to quantize space-time itself, suggesting that space may be made of tiny, discrete units. In some loop quantum gravity models, the black hole singularity might be avoided. Instead of a point of infinite density, you get a bounce, where space-time curves enormously, but then rebounding occurs, potentially connecting to a new region of space or another universe. If so, perhaps the interior of a black hole could connect to somewhere else through this quantum bridge, effectively making something like a wormhole or a white hole as the other side of the black hole. These ideas are speculative, but they share a theme. Quantum effects likely save us from the infinities and paradoxes that classical general relativity predicts. Black hole thermodynamics teaches us that a black hole's event horizon behaves like something with microscopic structure. It can store information and has a kind of granular nature when viewed through the lens of quantum theory. This hints that space-time itself has a microscopic, quantum structure. Much as a smooth steel ball is actually a lattice of atoms, if you look closely, the surface of a black hole might be composed of tiny quantum bits of area. That would explain why the entropy, number of bits of information, scales with area, not volume. The information content is on the surface. All these insights are arrows pointing toward a future theory. We do not have that theory complete yet, but black holes have been generous with clues. By studying them, theorists discovered deep links between gravity and thermodynamics, formulated conjectures about the holographic nature of the universe, and tested ideas of quantum gravity in thought experiments and simplified models. In a way, black holes are to theoretical physics what the Rosetta Stone was to archaeology, a cipher through which a new language, quantum gravity, can be decoded. They push our understanding to the breaking point, forcing us to invent new concepts to describe what happens under such extreme conditions. One day, if a full theory of quantum gravity is achieved, black holes will likely be central in its narrative. In that theory, black holes will no longer have singularities in the sense of infinities. Something will replace that pit of endless density, perhaps a churning quantum foam, a tangle of space-time filaments, a doorway to another domain, or something we haven't yet conceived. And that theory will elegantly show how information, gravity, and quantum behavior reconcile. Until then, black holes remain our greatest teachers in the quest for unity in physics, hinting at the grandeur of a universe where all forces and particles dance to a single tune we have yet to fully hear. Black holes also capture our imagination, not only for what we know about them, but for the tantalizing possibilities they suggest. Could a black hole be a door to somewhere else? What lies beyond the confines of the event horizon? Is it just oblivion, or might it connect to something unexpected? These questions straddle the boundary between science and philosophy, between rigorous theory and speculation. One concept that arises from the mathematics of general relativity is the white hole. If a black hole is a region where nothing can escape, a white hole is the opposite, a region where nothing can enter, from which matter and light can only emerge. In effect, it's the time reversal of a black hole. If you take the equations for gravitational collapse and imagine running time backward, you get a white hole. Such an object would constantly spew out anything that ever fell into its black hole counterpart in the past. It would be like a cosmic fountain, an out-only region of space-time. While intriguing in theory, white holes have never been observed, and most physicists doubt they actually exist in our universe. They appear to be unstable. Any disturbance would turn a white hole into a black hole. Some have whimsically wondered whether the Big Bang itself, which spewed matter out of a singular point, was a kind of white hole. But that idea is more poetic analogy than testable theory. For now, white holes remain a mathematical curiosity, a reflection of black holes in the mirror of time, with no evidence that nature ever chose to make one. Even more captivating is the idea of wormholes, tunnels through space-time that could connect distant parts of the universe, or perhaps different universes entirely. This concept originally arises when one studies the geometry of a non-rotating black hole. Mathematically, the complete extension of such a solution hints at a bridge connecting two regions of space-time. This bridge was dubbed a wormhole, or more specifically, an Einstein-Rosen bridge. However, that particular wormhole is not traversable. It pinches off too quickly for anything, even light, to pass from one end to the other. It's like a tunnel that collapses before you can get through. But it planted the seed of an idea, perhaps under the right conditions, say, with a rotating black hole or with the addition of exotic forms of matter. A stable, traversable wormhole might exist. A traversable wormhole would essentially be a cosmic shortcut or portal. You enter one mouth of the wormhole and emerge from the other mouth at a distant location or a different time. It's the stuff of countless science fiction stories, a convenient tunnel through space and time. Physicists have explored the wormhole concept with equations. The consensus is that if wormholes are possible at all, they likely require exotic matter with negative energy density to hold them open. Otherwise, the tunnel collapses into a black hole, white hole pair. We don't know of any way for such negative energy matter to accumulate naturally, though quantum effects can create small regions of negative energy. So traversable wormholes remain hypothetical. If one did exist, a traveler falling into one end wouldn't hit a singularity. Instead, they'd feel gravity's pull and some extreme tidal forces. Then, in theory, emerge in a completely different region of space-time. The journey might be short, even though the separation in normal space could be immense. No evidence for any kind of wormhole has been found in the universe. We have not seen stars disappearing in one location and appearing elsewhere, or strange lensing effects that would indicate a shortcut in space-time. But intriguingly, modern physics, especially in certain speculative quantum gravity theories, often finds wormholes cropping up in math, sometimes tiny ones at the Planck scale, forming a space-time foam, or connections between black holes and entangled particles, as in the thought-provoking ER-as-EPR conjecture, which suggests a link between wormholes and quantum entanglement. It may turn out that wormholes exist, but are either microscopic or effectively inaccessible, or they may not exist at all, and nature may enforce cosmic censorship that prevents such causal shortcuts. Then there is the idea of extra dimensions. Some theories, notably string theory, suggest that our universe might have more spatial dimensions than the three we directly experience. These extra dimensions could be curled up at small scales, or we could be confined to a three-dimensional brain within a higher dimensional space. If extra dimensions exist, black holes could potentially take advantage of them. For instance, in certain models with large extra dimensions, a black hole could leak gravity into those dimensions and evaporate faster, or high-energy collisions, like those in particle accelerators or cosmic rays, might produce microscopic black holes. There was even a brief flurry of public concern before the Large Hadron Collider turned on, when people wondered if it could produce a black hole that would swallow the Earth. Physicists responded that if the collider could make tiny black holes, which was considered possible in some speculative models, those black holes would evaporate almost instantaneously via Hawking radiation. Indeed, no such micro-black holes have been observed at the LHC, putting limits on those theories of extra dimensions. Extra dimensions also allow for exotic objects, like black strings or black rings, in higher dimensional gravity. But those are beyond what we could detect in our 4D space-time shadow of the full reality, if such reality exists. Some have speculated that perhaps what we see as a black hole is only part of a higher dimensional object, like the 3D cross-section of a 4D black hole, analogous to how a 3D object passing through a 2D plane appears as a changing 2D shape. It's a wild idea, but it underscores that black holes force us to think outside the familiar. In the realm of speculation, one can imagine fantastical scenarios: falling into a black hole and popping out of a white hole in another universe, or black holes being gateways to time travel, since moving through a wormhole could in principle allow backwards time steps under relativity. These remain squarely in the hypothetical. Our current understanding says that if you jump into a black hole, you will be shredded by tidal forces and then crushed at the singularity, not transported to a wonderland or mirror universe. Every physically reasonable analysis suggests that a trip into a known black hole is a one-way ticket to destruction. Still, the fact that our theories allow such curious solutions at all, white holes, wormholes, higher dimensional holes, is food for thought. They haven't been realized, as far as we know, in our universe, but they tell us the space of possibilities is vast when dealing with gravity and quantum law at extremes. The speculative frontiers remind us that black holes sit at extremes where our knowledge frays. Could a black hole ever turn into a white hole, spewing everything back out in a final cosmic act? Could two black holes be connected back to back as an intergalactic subway tunnel? We find no evidence for these outcomes, but considering them stretches our thinking. In the end, whether these exotic ideas hold any truth or are just mathematical quirks, exploring them deepens our appreciation for how strange the universe might be and how much more we have to learn. Black holes push us to ask, what if, at the grandest scales? And that question is the seed of discovery. Few phenomena illustrate the relativity of time and space better than a black hole. What a black hole does to time is as dramatic as what it does to light. To understand this, consider three vantage points. 1. An intrepid, and perhaps doomed, astronaut falling into a black hole. 2. A distant observer watching that fall from afar. And 3. A spacecraft trying to orbit close to the black hole without crossing the horizon. For the person who falls in, the journey is surreal, but not in the way one might expect. If the black hole is huge, say, the one at the center of a galaxy, our falling astronaut might not feel anything particularly special at the event horizon itself. No dramatic jolt or sudden change. There's no signpost in space saying, "You are now entering the black hole." To the falling astronaut, space still looks black in all directions, and local physics still behaves normally, aside from the intense gravity. However, as they continue inward, gravity's tidal forces grow inexorably. If it's a smaller black hole, these forces become lethal well before the horizon, stretching the astronaut into a thin strand of matter long before they reach the horizon. But in a supermassive black hole, they might actually cross the horizon intact, and only later, much deeper in, feel those catastrophic tides. No matter what, once inside the horizon, all paths lead down to the center. Our falling astronaut cannot avoid the singularity. Moving forward in time means moving closer to the singularity at the core. From the astronaut's own perspective, they reach the singularity in a finite amount of time. Their clock ticks along normally. Perhaps they have only hours or minutes from crossing the horizon until they meet the central doom, depending on the black hole's size. Now consider the distant observer, watching through a telescope as their friend plunges toward the black hole. To this observer, the story looks very different. As the astronaut approaches the event horizon, the distant watcher sees their motions slow down, as if someone hit a cosmic slow-motion button. The astronaut's clocks appear to tick ever more sluggishly. If the astronaut waves or flashes a light in a regular rhythm, those signals come out stretched in time. The light from them shifts to redder and redder wavelengths, a gravitational redshift, quickly fading out of visible sight into infrared, then radio, then silence. In fact, the distant observer never truly sees the astronaut cross the event horizon. Instead, the astronaut appears to approach it ever more asymptotically, slowing to a crawl and growing dimmer, their image eventually smearing into a faint red ember and then vanishing. To the outside world, the astronaut becomes essentially frozen on the edge of the black hole, taking an infinite time, from their perspective, to actually fall in. Of course, in reality, the astronaut does fall in and meets their end, but no information from that tragic fate can reach the outside. So from the external view, the fall looks never-ending and incomplete. The astronaut's image is stuck on the threshold. This discrepancy isn't a contradiction. It's a manifestation of how time and light behave near a black hole. Time itself flows at different rates in different places when gravity is strong. At the event horizon, outgoing light is so redshifted and delayed that to an outsider, it effectively never emerges. Meanwhile, for the infaller, their own time is perfectly normal as they experience it. Relativity allows each perspective its own reality, and only a synthesis of them gives the full picture. Now imagine a third scenario. An observer who doesn't fall in but tries to orbit or hover close to the black hole's horizon without crossing it. This observer will experience time in an unusual way as well. Their time runs slower relative to someone far away in weaker gravity. Suppose they orbit precariously close to the horizon for what they measure as an hour, and then return to a safe distance. They might find that many hours, or days, or years, depending on how close and how fast, have passed in the rest of the universe during their excursion. They have essentially traveled to the future. This is a genuine effect of time dilation near a black hole, also seen, to a far lesser extent, near any massive body like Earth. In principle, a sufficiently advanced civilization could use this effect for time travel to the future, go park near a supermassive black hole for a while, then come back to find civilization much further along. It's the scenario famously illustrated in science fiction, such as the movie Interstellar, where minutes near a black hole equated to years back on Earth. Orbiting near a black hole also gives a front row seat to some optical oddities. Light from the rest of the universe doesn't follow straight paths near a black hole. It curves and swirls. An observer close to the horizon might see the entire sky above warped into a small, bright ring as light from all around gets bent into their view. They might even catch a glimpse of the back of their own head, theoretically, because light can orbit the black hole too. There is a particular orbit called the photon sphere, about 1.5 times the horizon radius for a non-rotating black hole, where light can circle the hole. An object behind the black hole relative to you might have its image loop around and appear in front of you, perhaps multiple times, each fainter and more distorted than the last. The visual distortions would be extreme, as if space itself were a hall of mirrors. This interplay of perspectives around a black hole is not just a trick of viewpoints. It's a profound demonstration that space and time are fluid, dynamic, and relative. To the person falling in, crossing the horizon is uneventful, but their end comes quickly. To the outside person, the fall never completes, and the infaller fades away. To someone orbiting nearby, time slows, and the outside universe's clocks speed up, and the view warps fantastically. All these narratives are true in their own frames of reference. What does it mean, philosophically, that time can stretch and skew so much? Black holes force us to abandon the notion of a universal, absolute time. Each vantage has its own time, and gravity weaves them into a tapestry where no single thread is privileged. It's a reminder that our intuitions, born of everyday experiences, are woefully inadequate for cosmic extremes. If one were writing a story of a fall into a black hole, it would be a tragedy from the hero's viewpoint, an eternal suspense from the audience's, and a bizarre odyssey from a nearby companion's, and all would be correct. Ultimately, whether you watch from afar or take the plunge yourself, black holes underscore the relativity in relativity. They stretch our understanding of time and causality, proving it can be as pliable as taffy under the right conditions. They give us scenarios where two seemingly opposite statements, the astronaut fell in and died in seconds, versus the astronaut never fell in even after eons, are both true in their own contexts. The reconciliation lies in the mathematics of space-time, but described in plain language, it remains one of the strangest features of our universe. Not all black holes sit majestically at galaxy cores or announce themselves by tearing stars apart. Some are drifters, wandering the cosmos unseen. These are the rogue black holes, solitary, star-sized black holes that have been flung free of their birthplaces or left isolated in interstellar space. They roam the galaxy like invisible phantoms. How does a black hole go rogue? One way is through gravitational slingshot events. In the chaos of a dense star cluster or a galaxy's core, interactions can kick a black hole out of its nest. If a black hole was once in a binary system and its companion star went supernova, the explosive kick could send the new black hole hurtling away. Or if two galaxies merge and their central black holes coalesce, the newly merged black hole can receive a recoil, a kind of gravitational kick, from the asymmetric blast of gravitational waves, potentially ejecting it from the galactic center. There are also scenarios where multiple black holes in a cluster have close encounters that fling one of them outward at high speed. Over cosmic time, these processes have likely populated our Milky Way with wandering black holes. These nomads are virtually invisible. A black hole without a companion or accretion disk emits no light. It's as dark as a chunk of pure night, gliding through space. To detect a rogue black hole, we must rely on its gravitational effects. One telltale sign is microlensing. If a black hole passes in front of a distant star from our viewpoint, its gravity can bend and magnify the star's light. We would see the star momentarily brighten or shift in position, even though no object is visible. By carefully monitoring millions of stars in the galaxy, astronomers have caught a few such events, and some are best explained by free-floating black holes. Indeed, astronomers recently found strong evidence for an isolated black hole roughly 5,000 light-years away. Over the course of months, a background star's apparent position and brightness were distorted in a way that indicated a compact object of about 7 solar masses passing in front of it, likely a lone black hole. That dark traveler, a remnant of a long-ago supernova, drifts through the Milky Way's spiral arms, unaccompanied by any star, effectively a ghost. And our galaxy may harbor millions more like it. For every massive star that died and didn't get kicked into a tight binary, a lone black hole could be roaming. Could one pose a danger to us? The idea is a staple of science fiction horror, an invisible destroyer moving silently through space. In reality, space is enormously vast, and even millions of rogue black holes are spread thin. The odds of one coming close enough to our solar system to disrupt planetary orbits are exceedingly remote. But the concept is chilling nonetheless. A rogue black hole could drift just a light year away, and we might barely notice, except that some stars would wobble oddly, or lensing events would spike in its vicinity. These solitary black holes likely have subtle effects. As they wander, if one passes through a nebula or molecular cloud, it might capture a bit of gas, creating a brief accretion disk and a flash of X-rays, a momentary flare betraying its passage. If one eventually slows down through dynamical friction and settles in a galaxy's halo, it might one day encounter a star and capture it, becoming visible as an X-ray binary after eons of solitude. We haven't observed such a transformation yet, but it's within the realm of possibility. In a poetic sense, rogue black holes are cosmic Ronin, masterless, traveling from one gravitational domain to another. Once the core of a bright star or a member of a binary partnership, now they are alone, carrying the mass of a sun in a package the size of a city, with only their gravitational pull as a calling card. They remind us that the universe has dark wanderers and lost souls, not just the organized systems we easily see. When we gaze up at the night sky, we might imagine that among the glittering stars and nebula, there are also these dark interlopers moving silently. They add a layer of mystery to the galaxy, unseen mass in motion. Only through careful observation, Catching the slight bending of starlight or detecting the faint tug on a star's motion, can we even infer they are there? The vast majority will likely remain unknown to us, blending into the darkness. The era of routinely observing rogue black holes may still be far off, but simply knowing they wander out there expands our sense of the cosmic wild. It reminds us that for everything we see, there is much we don't see, and sometimes the most powerful things announce themselves only by their absence or by a whisper of gravity. The Milky Way becomes a more intriguing place, populated not just by stars and luminous phenomena, but also by these dark, drifting punctures in space-time. They are the quiet counterparts to the roaring quasars and X-ray binaries, a silent population of the fallen. Black holes have been part of the universe's story from the early chapters. They are not just endpoints of the stellar life cycle today. They were present in the cosmos's youth and have helped shape cosmic history. In fact, one of the great challenges in modern astrophysics is explaining how supermassive black holes managed to form so quickly in the early universe. Not long after the Big Bang, before even 1 billion years had passed, we see evidence of quasars, incredibly bright galactic centers powered by black holes of billions of solar masses. For such a black hole to exist so early, it must have grown very fast or started from a very large seed. The first stars, the so-called population 3 stars, formed perhaps 100 to 200 million years after the Big Bang. These stars were likely very massive, hundreds of solar masses, due to the pristine, metal-free gas conditions, and when they died, some would have left black holes, maybe tens of solar masses. These were the universe's first black holes, the embers of the first stars lighting up the cosmic dawn. If one of those early black holes found itself in a dense region, like the center of a small protogalaxy, it could feed on gas and merge with its neighbors, growing larger over time. Still, going from, say, a 50 solar mass seed to a billion solar mass quasar in a few 100 million years is no small feat. Some mechanisms might have helped. Perhaps some of those first stars were so massive, imagine a single star of 100,000 solar masses, that they collapsed directly into a black hole of, say, 10,000 solar masses, skipping the step of supernova and neutron star entirely. Such a direct collapse black hole would give a huge head start. We call these hypothetical giants direct collapse black holes, or quasi-star remnants. The idea is that in the early protogalaxies, if cooling was inefficient, due to lack of elements like carbon or oxygen that aid fragmentation, a huge cloud could contract without breaking into many stars, forming one megastar or an unstable disk that funnels mass into a central black hole seed. Another assist could have come from galaxy mergers. The early universe was smaller and more dense. Proto-galaxies collided frequently. If each had a black hole seed, those holes could sink to the center of the new, merged galaxy and eventually merge with each other. Each merger could produce a bigger black hole, and potentially a kick, though if the galaxy is massive enough, the black hole may remain bound. Also, the tumult of mergers would drive lots of gas toward galactic centers, providing a feast to fuel rapid growth, a phase we might identify as a bright quasar. So a combination of moderately large starting seeds and frenzied early feeding could yield a billion solar mass black hole by the time the universe is, say, 700 million years old, which is what we observe. Primordial black holes, as previously discussed, are another candidate for seeds. If any relatively large ones formed in the Big Bang's aftermath, they could start growing even before the first stars. But the evidence for primordial black holes as a significant population is not there at the moment. It remains a theoretical possibility. What we do know is that by the time the universe was 1 billion years old, it already had black holes that qualify as monsters by today's standards. These early black holes likely had a profound impact. They would have been pouring out radiation and perhaps launching prodigious jets, affecting their host galaxies and maybe even the intergalactic medium around them. The epoch of ionization, when the universe's hydrogen was ionized by the first light sources, might have contributions from quasars, not just young stars. Those early black holes were not quiet spectators. They were actors on the stage, possibly shutting off star formation in their host galaxies, even as those galaxies were still young. As time went on, the universe expanded and evolved. The rate of galaxy mergers slowed. Star formation settled into a slower pace in many galaxies. The supermassive black holes that had grown so rapidly early on then often calmed down, having consumed most of the nearby fuel. Our Milky Way's black hole, for instance, is relatively starved now and only occasionally snacks on a passing gas cloud. But we see its active past indirectly in the massive bubbles of gamma ray emitting gas blown above and below the galactic center, likely a sign of an energetic phase millions of years ago. Understanding how black holes formed in the early universe helps complete the picture of cosmic history. The first black holes were both products and agents of cosmic evolution, products of collapsing matter in a young universe, and agents that influenced the formation of galaxies and stars around them. When we look at the farthest quasars, we are peering into a time when the universe was in its teenage years, full of energy and growth spurts, with black holes growing like weeds. In a sense, the evolution of the universe and the growth of black holes have been entwined threads from the very beginning. Today, billions of years later, the universe has many matured galaxies with central black holes that grew in that earlier frenzy and then went quiet. Those black holes serve as archaeological evidence of that formative epoch. They are giant scars of the early universe's creativity and violence, much as mountains and craters tell us about Earth's geological past. By studying the distribution and masses of black holes in distant quasars versus those in local dormant galaxies, we glean insights into that long-ago time. So black holes teach us not only about gravity and quantum mysteries, but also about our cosmic origins. They have been there since the first stars died, and perhaps even earlier. They are the storytellers of the universe's youth, holding in their existence the tale of how gas clouds became galaxies and how tiny instabilities grew into mighty structures. Each massive black hole in a distant quasar is like a messenger from that dawn, saying, "I was here, shining brightly when the universe was young." Through them, we study not just black holes themselves, but the dawn of structure and the rise of cosmic order out of chaos. In confronting black holes, we find ourselves confronting the very limits of understanding and reflecting on deep questions about identity, destruction, and the fate of information. Black holes are often seen as the universe's ultimate agents of annihilation. They swallow light, time, and anything else that crosses their threshold, seemingly erasing all traces of those objects from our universe. In that sense, a black hole is a kind of cosmic death, the death of a star, the death of information, the end of a path. Standing before a black hole's event horizon, one can't help but draw parallels to concepts of an ultimate point of no return. Yet, what black holes have taught physics is that endings may not be as absolute as they appear. The paradox of information, whether information that falls into a black hole is lost forever, forces us to reconsider our notion of destruction. Quantum theory tells us that information is never truly destroyed, even if it is hopelessly scrambled. So if even a black hole ultimately cannot obliterate information without a trace, as many physicists now suspect, then perhaps nothing is ever completely lost. This is a profound and somewhat comforting thought, that the essence of things, the information that defines them, has a way of enduring, even in the maw of a black hole. Think about the no-hair idea. Two very different stars, one a blue supergiant and one a red giant, could collapse into black holes of the same mass and spin, and then be indistinguishable from the outside. The individuality of the stars, their hair, is gone. The black hole does not reveal what it has consumed. This sounds like obliteration of identity, and classically it is. But if the modern view is correct, the information isn't truly destroyed. It's just hidden in correlations in the Hawking radiation or imprinted somehow on the horizon. In a poetic sense, one could think of it as reincarnation in code. The pattern that was a star is diffused into the universe at large over eons, via subtle encodings in radiation. No one could practically reconstruct it, but it's not utterly erased from existence. Black holes also resonate with the concept of death and rebirth in another way. The death of a star gives birth to a black hole. The chaos a black hole causes can lead to new stars forming as jets compress gas or as mergers shake galaxies. In a long time frame, a black hole might evaporate and return its mass energy to the universe, in essence, completing a cycle. This parallels natural cycles we see elsewhere, say, a forest fire that destroys yet returns nutrients to the soil from which new life springs. It's as if black holes are part of a grand cosmic recycling program, albeit on scales of time and energy far beyond everyday comprehension. Moreover, black holes force humility about knowledge. The interior of a black hole is fundamentally unknowable to an outside observer. It's cut off causally from the rest of the universe. This is a bit like our own mortality. Whatever lies beyond the horizon of death is not accessible to the living. Black holes give that abstract idea a concrete form, a region from which no information can reach us. In that way, they are like a physical embodiment of mystery. One stands on the outside and wonders, but cannot see inside. It's a reminder that there may always be horizons beyond which our empirical knowledge breaks down. Yet, rather than simply signifying despair or the futility of effort, black holes have inspired humans to unprecedented feats of discovery. We did not throw up our hands at the sight of an information horizon. We built theories and experiments to get as close to it as possible. We figured out how to image an event horizon's shadow and how to detect the ripples from events beyond a horizon. In a sense, we've learned to navigate around the edges of the unknown and glean truths without directly peering inside. There's something uplifting in that. It suggests that even if some things are fundamentally inaccessible, we can still learn about them indirectly and push the veil a little further back. Black holes also bring forth existential metaphors. The idea of an event horizon can be seen as analogous to moments in life beyond which things are forever changed, a point of no return. Dropping past a black hole's horizon is a one-way journey, much like certain decisions or events in life, or the act of death, are one-way. The philosophical question arises, is there anything beyond that one-way journey? In black hole physics,